Good morning, ladies and gentlemen. On behalf of Leadvent Group, let me welcome you on our day 2. I hope you had a restful night, that you did some networking during our reception, and that now you are ready for the second day, which will be also packed with a lot of presentation. The organization logistic is basically the same as yesterday. All the coffee breaks will take outside in the lobby. For the lunch, we will go for the in the restaurant downstairs. And then, as said, you will also receive the presentation in 2 weeks' time after our speakers will make the necessary amendments. Also, our chairman is same as yesterday, David Morgan, and I will be keeping you updating about any possible changes in case there are some last-minute amendments to the agenda. Also, I would like to remind you to fill out the evaluation form where you can rate our speakers, the organization, and everything. And now, as yesterday, David, the floor is yours. Thank you.
Good morning. I hope everyone had a pleasant evening, good dinner, and you were also stimulated by the discussions yesterday. You went back to your hotel room, wrote a peer review academic paper. It's already published in a journal somewhere, and you took advantage of the conversations that we've been able to have. Because that's what we need to do, right? We need to be provoked and challenged to think about how we can do what we are doing better and how we can encourage our peers and colleagues to do the same thing. As we talked about yesterday, we have, as you've probably heard the phrase, an embarrassment of riches, right? In this room and the colleagues that you are surrounded around, we are the ones and others that we know who can make those differences and make those changes in the circular economy space for polymer composites and whatnot. So please really help each other challenge on how we can move this discussion along, both today and then after we leave. So this morning, we will start off with end-of-life wind turbine blade sustainability implications. We have a few individuals like our moderator, Professor Vasilios Koustos from University of Edinburgh, whom we met yesterday, who will be moderating virtually. And then we have a couple of other virtual individuals, and then some are here present that will be up on the stage. So if you're in this next session, would you please come up for the panel? And then we will kick this off. And Professor Koustos. There's Mitch in space again. Vasilios, good morning.
Good morning. Good morning.
So the panel is ready. The floor is yours.
Okay, very good. Thank you. So here we are on the second day, and this will be a panel discussion about end of life of wind turbine blades, and we will be focusing on the sustainability implications. I suggest that we start a little bit with introducing again ourselves. For the people that have not seen us on the first days, and I can see that some of the panel members are going to speak later. So I think it's useful to introduce ourselves. My name is Vasilios Koutsos. I'm a professor at the University of Edinburgh, the School of Engineering. I'm working on material science and engineering with a focus on recycling and sustainability issues.
Yes, I can introduce myself. I'm Albert ten Bussen. I'm associate professor at Windesheim University of Applied Sciences.
Hello. Well, I introduced myself yesterday, but just in case, my name is Marta Barreras. I came from Rennercycle, a small company in Spain, and we are dedicated to dismantle wind farms mainly.
Hi, I'm Ana Teresa Lima. I am a senior researcher at the Technical University of Denmark, particularly to make a distinction of other colleagues here. I am from DTU Sustain, which is the Department of Environmental and Resource Engineering, particularly the section of materials and durability. And I work a lot with construction materials, and you'll see later in the presentation that we try to use some of the ways to valorize it in construction materials. That's what we do in the Blades to Build project.
Hi everyone, I'm back. I'm Mitch Renchek. I'm from the Electric Power Research Institute. EPRI is a nonprofit research organization. Recapping just in case some of the folks weren't in the room yesterday, we are typically funded through asset owners and utility companies throughout the world. Probably roughly around 90% of the utility companies in the US fund EPRI research in one way or another. At EPRI, I lead our end-of-life management for wind energy technologies research. And so what that looks like is end-of-life management research that is focused for the asset owner. So we do a lot of decommissioning research, a lot of recycling technology evaluation, really trying to help our members navigate the throes of end-of-life management of their wind assets, especially wind turbine blades, as of the past 3 or 4 years. Thank you.
Okay, very good. We are 5, as far as I can see, all together. And perhaps we can start by saying a few words about a little bit the definition of end of life, because it might not be absolutely obvious to everybody. End of life might come from a lot of reasons. I wonder if Albert can say a few words about this based on his experience, when the end of life comes.
Yes, that's a good question. And sometimes it's confusing because the material is not always at the end of its life, but at the end of its use. So there are two ways to consider. You can look at the end of the function of the material, so the end of the use, but then, not the material is worthless at that stage. Often it is not, because composites last very long and do not corrode. But generally, also for easiness, it's best to use one term, I think, and use the term end of life, which comprises also end of use, and maybe you can reuse the material because it still has its worth. So I hope this gives a little bit clarity.
Yeah, and I understand. It could very well be that some parts of the whole constructions are absolutely fine, but some key parts have stopped to be financially viable, to be repaired all the time. New technologies are coming, and I think we kind of agree that the end of life for the wind turbine blade systems that we are mainly talking in this meeting is between 20 and 30 years.
Yeah, I think that is the normal lifetime, or well, the time of use of a rotor blade. I don't know how it is in the different countries, but in the Netherlands, it is about 20 to 25 years. But maybe in other countries, it can last longer. I don't know.
That's about sorry, I'll chime in.
Yeah, Mitchell. Yeah.
Yeah, that's about the same as it is in the US, going off of a 20 to 25-year design life. That's typically how long asset owners will plan to run it. Even if they could get some more life out of it, that's what they plan for in the installation phase. But I will add, due to tax incentives in the US, oftentimes repowering occurs at 50% of that design life, even more than 50%. So they're posed with an issue of getting a production tax credit and building either new assets or just reinstalling some of the pieces that can be upgraded, which is often the blade, since that technology develops a lot faster than some of the other technologies within the wind turbine. So oftentimes we'll see blades only last around 7 to 10 years because of our tax incentive structure over in the US. So just wanted to throw that in there as well, because it's not, while it's designed for 20 to 25 years, it doesn't always hit that mark. And the blade reuse market in the US is, I'll say, non-existent. So it usually needs to get managed.
Okay, very good.
Well, sorry, I would like to add.
Go ahead. Yes.
Yeah, that at the beginning, when the it's like an echo, and sorry, I will try. There is like kind of an echo, and I hear me twice. Well, I will try again. That at the beginning, when we designed the wind turbines that are
You are muted now. You are.
No.
Yeah. Okay.
Hello?
Yeah.
No?
Yeah. Now I can hear you. Yes.
I will try again with the echo. Well, I would like to say that at the beginning, when we designed the wind turbines in the 19th, in the first and in the earliest 2000, we designed for 20 years all the turbines components in general. But now they are still operating, and without proper maintenance, they can extend the lifetime of those wind turbines, the components, even until 30 years. But now, with the new designs that are bigger, larger, we see that those this lifetime is not so long, and we are seeing problems, I think maybe due to the flexibility of the materials, because the blades are bigger, and that they fail just before the expected, depending on the site conditions as well. But we are seeing indeed in the industry that these larger blades are failing before the 20 years life.
Very good.
So
Very good.
to chip in
Yes.
here as well.
Yeah.
if I may.
Please. Yes, please.
Okay, you are muted now. Just saying.
I'm muted. I'm not
You're
muted.
muted. Yes.
I'm not muted.
Oh, it's from him. Oh, okay. It's about the repowering.
Can you hear me? Can you
so
hear
no
me?
long-
Can you hear me?
Yeah.
Okay, good. I was not muted. I don't know what happened. Sometimes there might be breaks. Okay.
Just to complete with the repowering, because yes, it's interesting to know that the bigger blades are failing, but also that the not so end of life blades, the smaller ones are also being taken down for repowering, right? So
Very good. And what about the avenues for what's going on after the end of life? Now, let's go. Let's start with you. Your views regarding the repurposing, reusing, and recycling of the items. What do you think are the most important things here? I know it's a very open-ended question, but just what do you think that is more important? Yeah, you can
Yes,
start. Yeah.
I cannot follow completely all the end of life rotor blades, and I don't know where they end. Some end in a proper way, for instance, in a co-processing, but many of them are also burned, incinerated, or shipped to another country, so sold. But it's not very clear where they all end. And in fact, if you would follow the legislation in the Netherlands, they should be used in a proper way, either co-processing or to a certain expense. And then it is allowed to burn. But this path is not followed always. And so there's a kind of a side path that they can be burned without any official approvals.
If I may jump in.
Yes, please.
From a circularity perspective or from a resource efficiency perspective, we should aim always at higher R's. And I'm not sure if everybody follows when I say that. But
please explain the people.
Okay, in the circular economy framework, there are different R's. I will have this later in one of my slides, so I can focus there a little bit and explain it if it's interesting. So higher R's aim at maintaining the product in the use phase for longer. So that's ideal. So you're wasting less resources, less materials. You're being more efficient. So every time we go to lower R's, like even recycle, repurpose, there are endpoints that are not, from a resource point of view, that efficient. So.
Very good point. Very good point.
So this is theoretical.
Yeah. So always we'll have
on that one as well, if you don't mind.
Yeah. Go ahead.
Yeah, so I'll put the asset owner hat on real quick, and from that perspective, it usually boils down to two components in terms of what pathway to be utilized for end of life blades, and it's not really, I mean, it's about the technology, but it comes down to cost and risk associated with each technology that an asset owner might be choosing. So if they have things across the board, it's likely gonna boil down to those two. And then after those are satisfied, usually other factors will chime in, thinking more in terms of sustainability. Okay, we'll consider how much water is it consuming, how much carbon is it emitting, how much eutrophication is it increasing, and things like that. So those are probably the two greatest things that I hear when I talk with a lot of utility companies and asset owners on, why did you choose that specific recycling technology? And they're like, oh, well, we audited it. We went through a really intensive assessment of the technology. We've had a lot of meetings. We've gotten a lot of material, and then we're pretty close in proximity to the recycling facility. So that means our transportation costs were pretty low. The tipping fee maybe was a little more competitive than some of the others out there. So it's usually a combination of those two things is how the decision gets made oftentimes from the people that I engage with and talk to on this subject.
Excellent. Very good points. Marta?
Yeah, I think that as Anna commented, the most important thing is to keep in use the materials. with life extensions of the wind turbines and so on. But this life, even though it's not infinite. So if you go to the second step, we need repurposing, for example. But here again, we don't have a big market. We are talking about just to use these blades for furniture, for example, or construction in terms of decoration, these kind of things, fancy things. They have a limited market. So in this sense, we need to go to the following step, just to invest in the technologies for recycling. We have seen yesterday here different technologies. I need that this is our more important challenge, just to continue working on that with the different ones, with the chemical, the thermal, just to go ahead and just to mature these technologies and being able to scale up, because as we saw yesterday, we are expecting a huge amount of blades in the commission blade in the following years. So we need to find a proper solutions to give an output of all of this material.
Okay, very good points as well. I was in another meeting a few months ago, and I remember the asset owner saying that we are desperate, and we will. But the issue of transportation is important for us. We will go with whatever is closer to our facility. At the end of the day, we're not experts on the difference on the different recycling methods, but if there is one next door, we will go to that. Which I thought that was an interesting comment. And perhaps what we need is smaller facilities, but more of them distributed in many geographically. Anyway, I'm looking at the bullet points that we are supposed to be covering. I think we covered several of them already, but I would like to ask you for anyone to chip in to share a bit about the challenges in collecting and dismantling the wind blades. If anybody wants to talk a little bit more about that.
Well, I can start if you want, because we the
Please,
commission wind farms.
Yes, please.
And well, there are many challenges here. The first one is the location of the wind farms, because when we are decommissioning the current all wind farms, they are in the best spot of the countries. They were the first ones, so they are in the top of the mountains with the best winds and so on. So
remote area. Yeah.
Yes, going there is difficult. The good point is that the wind turbines are smaller than the one that we have right now. So even though you need to transport the cranes and everything, and once you dismantle the wind turbine, there is another challenge here, that is the transportation of the blades. For example, in not all the locations you are allowed to cut the blade on site. Depend on the environmental regulations that you have in every country, in every region, I could say. So if it's possible to cut the blade on site, everything is more easier. But you need to be aware that with the different methodologies that we have, you can leave waste on the ground. You need to be careful about that. And that's why yesterday I was interested in some of the presentation. They were presenting the water jet cutting and this diamond saw technology that are the cleaners that I know. And then, well, the transportation will be easier in this sense. So for me, when it comes to the challenges relating to the dismantling on site, both of them are important to take into account.
Very good.
Yeah, I'll add to this
yes.
topic as well. I would say that the difficulty with dismantling just starts with how to bring the turbine blades to the ground. At first, in the U.S., we see probably two primary strategies: is taking it down with a crane, which is very controlled, and then we also see quite a bit of controlled ordnance being used to topple everything over, including the tower. So it all, you cut, you make a small cut at the base of the tower, put some ordnance on there, detonate the ordnance, and the whole thing comes over, and it's pretty efficient, and it's cheaper than using a crane. So that's why it's often opted for. You run into a lot of snags with the environmental aspect with that one, and so you need a lot more approvals. You need not only local authority approval, but you also need landowner approval, and sometimes that's a no-go. But in the U.S., I would say one of the greatest challenges with the dismantling is the transportation piece and the size of the blades when they're transported from the wind farm to the recycling facility. As the U.S. is quite big, and so there's a lot of miles to be traveled to get them to where they need to go to be recycled. So we've seen quite a bit of development in the U.S. with on-site shredding systems and companies that will perform on-site shredding after cutting blades into a few meter section on site. They'll shred it down into maybe a 7-inch piece and then transport that off-site. It's much more economical to do it that way rather than send maybe 10 times as many trucks for the same amount of blade material going to the same place. So that's a little bit of the trends that we've seen in the US in terms of dismantling blades.
Yeah, if I can add something here is that the components that they contain oil, there is a lot of careful handling there. I mean, you cannot open them up there. You have to bring them down. And the other thing is to take care also of the weather conditions. There is a need for very careful planning when you are doing the dismantling. Do you have anything to add, Albert?
Well, I'm familiar with the problems of breaking or getting blades into pieces because they are very, very strong. And we also were involved in trials to cut them by crushing or that kind of thing, but that's practically impossible. Only very heavy concrete crushers can crush rotor blades. But then you get a lot of dust, which is really an environmental problem. So at the moment, what we see in the Netherlands with the trials is that with a diamond rope type of thing or water jet cutting is the most cleanest way to do it. But I agree, you must try to cut the blade in smaller pieces to prevent very high logistics costs.
And if I may to add just something from the recyclers' point of view, I'll just phrase out some or voice out some of the discussions we had yesterday, which is there's also, the practical aspects that you just mentioned, but also the competing aspects that to get the blades to the recyclers. Not only landfill as when Europe has the document out asking for a ban, but also others that blades end of life blades that get exported outside of Europe, for instance, or that don't the blades that do not get to the recyclers.
I think this is a very good point that we need legislation to help that it is not going somewhere that it can be, get rid of more cheap. So we really need legislations, otherwise it's not possible to recycle or reuse in a proper way.
Yeah, because coming back to that, when we are talking about cost, but we are talking about paperwork. Because the blade, once you dismantle and going transport it to another place, you need to do a lot of paperwork because it's considered a waste. Even though it's the entire blade, it's considered a waste, and you need to give notice to the administration 10 days in advance to say that you are going to transport this. At least in Spain, the legislation in this sense is very strict, but even though they allow the disposal in landfill. So I agree that the first measure should be just to ban this landfill disposal.
Yeah, I fully agree with that. Yeah.
Okay, and we have seen that the legislation is not very homogeneous in the countries around the world and in Europe as well. There is a lot of variation in in the legislation. So this is something for you to coordinate probably. In the less than 5 remaining minutes, what I would like to do is to ask the audience if they have any particular questions to the panel for the items that for the subject that we have talked about.
You mean subjects that not are touched yet?
Or to what we have already said. If they have any questions regarding the end of life of wind turbine blades, the sustainability implications. I think we have covered a lot of points, but are there any clarifications from the audience, any particular questions? It will be, yeah.
Can I try? Okay. Yeah, thank you for guys. And I'm Merawan from Japan, and about the after demolition supply chain, we have the same issue, and it's even more serious than Europe because most of the onshore wind turbine located in the middle of mountain, and the road is always narrow and winding. And so after demolition, at least 57-meter or 6-meter blade is difficult to transport, and it costs once or when we construct that, it is asset, but once we demolish that is a waste. So we are searching for some effective solution to cut off water jet or 5-meter pieces, 6-meter pieces. That is good, but if more the chop into the small pieces on the site device is our ideal thought to reduce the demolition cost, so that asset owner will be more cost competitive for the project. So do you have any idea or device to chop into the pieces on site? European countries are mainly plateau, so I'm not sure that it's mandatory for European countries, but
Yes, well, in the Netherlands, we have a company that has an installation in their plant. But to do the shredding or the chopping on site is, we don't have such a thing, but I believe there are developments. I believe there's a Swiss company that does something like that. But we don't have it, and well, I think you need quite some insulation to move to the site where you demolish or you dismantle the windmill. And on offshore is coming, of course, especially in future, then it will be even more difficult, I think. So maybe it's better to make the blade a little bit smaller and then transport them onshore to an installation, for instance, at your company to process it further. But well, that's just an opinion.
Also to add the environmental and health aspects that can come from shredding it in place in situ.
In the U.S., folks use a wide variety of technologies to downsize blades on site prior to transportation. So I'm talking taking, a 60-meter blade and breaking it up into 6 10-meter sections, or even less, depending on how many cuts. But a lot of the technology that's used is usually a circular saw, a concrete saw, a wet saw attachment on the end of a skid steer or an excavator. And usually with those, there's oftentimes a dust suppression system that is integrated with the equipment, and that's just usually some type of water tank that's spraying water or wetting the saw as it's cutting to help keep the dust low. So that's one way that I've seen it done. And the other, again, is the on-site shredding, where these mobile shredding units are about the size of a semi truck, so they're not an oversized load. They'll fit on the roadways of the U.S. without any other permitting or any difficult or I would say any extra permits that you would need to transport it around. But those are very effective in reducing the size from around 10-ish meters to a couple inches. However, it does take a lot longer, so you have to add that into your total time for decommissioning, as it's a little bit slower. So those are the technologies that I've seen and I've heard of in the US that we use.
Very good. I think we are probably have approached, we have gone a little bit over time. Am I correct? I think we're about time to
We'll do
finish.
one more question with Claudia.
Okay, okay.
Hello.
The mic.
So
It should be on. Just speak and they'll turn it on.
Oh, this one. All right. Sorry. Yeah, the method to cut it on site, it's the first one that Mitch explained. And there's a couple of companies also in Germany actually who have developed that. So I can get you a contact and maybe you can then find out if they would be willing to kind of share the knowledge, or it's a big company. It's like 2,000 people. So it's not a small one, you know, who's just dismantling a little bit. So yeah, so I can get you a contact. So they have proven that it's you know, with the saw at the dust as an excavator, how it is actually, it's emission free, you know, it doesn't pollute anything on, you know, on the ground, not on the air, so it's pretty fine. And then I have a comment to the second message of Mitch actually is, you know, shredding on site is really a problem because that means you have no quality control whatsoever what's in it. So if anybody, because some dismantling companies or decommissioning companies have exactly the same idea. So, oh, let's shred it on site. Yeah, there's no quality control possible. We know that like 25 years ago, we put a lot of crappy stuff in the blades because everything was about functionality and just get the job done. You know, can we extend another meter, 5 meters and so on. So material health was not really a concern. So if we shred everything on site for companies like us, we will not accept any of that material because we don't know what's really in it.
Thank you for bringing this up because this is actually a very important point.
Very good.
Yeah,
So
indeed.
thank you.
Yes. Yep.
Thank you very much for moderating and to all the panelists who contributed. And so we'll be
And
moving
thanks
on
as
to our
well.
next section now. So thank you very much.
Cheers.
So Albert, you can stay. So as we discussed, he's associate professor at Windesheim University of Applied Sciences. Albert.
Thank you very much for your introduction. And my name is Albert ten Bussen. Already told that I'm assistant professor at the University of Windesheim of Applied Sciences in the Netherlands. And I will tell about our reuse method we developed. My background is the composite industry. I worked for 30 years in composite industry, starting with my function as in the glass fiber manufacturing and later on the design and production of composites. So I know how to make them, but now it's a question how you can reuse them. And we all know, well, this is something known to us all, that thermoset composites can last very long. They're corrosion resistant, very strong, so they have a long lifespan. So in this sense, they are very sustainable. However, they cannot melt, simply saying, after becoming solid. And that's for the traditional thermosets. And therefore, there is the big challenge that we are all gathered around to do something useful. And it's very hard to separate the composite into its original components, the individual fibers and the resin. So this is not very new, I think, to all of you. In the state of the art, as we see it, you have the possibility of the landfill, which is not very desirable, or incineration. There are developments on chemical ways to separate the components like solvolysis, pyrolysis. And there is an operational method, the co-processing method, cement kiln route as it is called. And this is an operational method, although it's an open loop method. So composites are not reused into composites again, but become part of cement. We have developed this reuse method, which is a closed loop method. That means that end-of-life composites are transferred into new composites. And with this method, we can cope with traditional thermoset composites. There are new developments, of course, which are very promising, like recyclable epoxies, the 3R resins or Vitermer resins that are recyclable. So this is very interesting. That gives a solution for the future. But also the injectable monomers, like for instance, the Elium resin of Arkema, that we also involve in our investigations, are very interesting because they can really result into recyclable composites. However, if we start today with them, we have to wait for the use of the product before we can benefit of this recyclability. So in the meantime, we need a solution for traditional thermoset composites. And we worked on this since 2015, and we scaled up to an industrial process with a good business case and sufficiently low footprint for CO2. And we did this together with several industry partners. So the principle of the method is to leave the composite intact because it has good properties, like mechanical properties, strength, and water resistance. In our methods, we machine the composite into smaller oblong pieces so that they can reinforce. We investigated to saw them in strips. However, this is industrially difficult with cost. So to our opinion, the shredding is the best way to do it and to make oblong flakes that serve as reinforcing elements in new composite products. We need to add virgin material, especially resin, to bind these flakes together, and some glass reinforcement at the outside. I come to that later. And we can make new, strong and water-resistant products that are ideal for infrastructural applications. We cannot make a new rotor blade again because for that our method does not give the right mechanical properties. So you could say it's downcycling. However, we think that we can make useful products. So that's positive. The starting point is to machine the end-of-life composite into flakes. It depends upon the composition, what type of flakes are obtained. When more random reinforcement is used, for instance, in boat hulls, then more plates are obtained. And when more oriented reinforcement is used in the product, like in rotor blades, then more spikes are obtained. So this gives a difference in these flakes. The LD ratio of the flakes that we use for a method is very important for the mechanical properties that can be obtained. And the LD ratio is the ratio between the length and the smallest dimension of the flake, which is indicated by D. And this LD ratio, we investigated this, has quite significant influence on the resulting mechanical properties of the new product. And this is not a new finding because this is also encountered with short fiber reinforced thermoplastics, that the LD ratio has especially a large impact on the mechanical properties of the compound. So we tested for different LD ratios, and the stiffness is not affected very much by the LD ratio, but the strength is. So you need an LD ratio of about at least 50 to get significant strength contribution of the flakes to the new products. There are more requirements on the flakes. They should be dust-free and they should be dry for being suitable for an industrial process. So on the left picture, you can see quite unsuitable flakes that are wet, dusty, and very big variation in sizes, and also very big chunks that are not really appropriate. The right photo gives good flakes that are made in a process with a company we cooperate, CRC in Rotterdam, and they make dust-free and dry flakes with a good LD ratio. We found that there are different processing techniques that are possible to reuse the composite with our method. However, for a real industrial, profitable process, pultrusion is the best option. It gives a limitation in your freedom of shape because you can only make profiles with a constant cross-section, but you can produce in a continuous way and cost-efficient. And then the cross-section of such a profile has a large core of these flakes that are bound together with the virgin resin, a mantle around it with random reinforcement to prevent crack initiation, and UD reinforcements. These are those blue lines because you need them first of all for the pultrusion process, otherwise you cannot cool to get the process running. But also it's a possibility, these UD's layers, for optimizing the product performance. We found that the core in combination with this outer reinforcement has a synergetic effect. So only the combination gives very high strength. If we replace the core with the flakes by foam, you get not that high mechanic strength. And if you would only test the core with the flakes, then the mechanical strength is impaired by crack initiation from the outside. So the combination we found is optimal. And we have done very much of testing also to make a structure of design philosophy according to, well, Eurocode that is now available for composites. This is technical specification 19,101. And in this design method, also the effect of moisture, temperature, but also creep and fatigue effects should be incorporated. So we did a lot of testing for that. Besides small specimen testing for these factors, we also did full-scale product tests to see whether it's really giving the well, especially the strengths that are found by design. And we made several demonstrators, full-scale demonstrators, like a retaining wall. We made 80 profiles of 3.5 meters length that we could vibrate into the soil, as is normally done with tropical hardwood. We made exactly the same outer dimensions as the tropical hardwood profiles, and they were vibrated in without any problems. Another demonstrator is use of guiding beams in a guiding structure near bridges, and we made beams of 4-meter lengths. You can see the cross-section on the left photo, and we have installed the lowest 2 rows of 4 of these structures with this. We also had to prove that it is safe for ship collision. There are some requirements on that, and we tested this, that it fulfilled before we could mount this on the structure. We also developed crane mats with this method, and it could withstand the harsh environments where they are used. However, the company that we are cooperated with would not like to proceed because they are afraid of microplastics claims in the future, because although the crane mat with the reused composite fulfilled good, of course there are some chips of material coming off, and the company is afraid of microplastics discussions. This is a pity, but we also made a bridge deck for heavy traffic bridge in the Netherlands. Also here we had to prove by calculations and by testing that it was safe. An industrial process, I told, is pultrusion. Then you get the high density that is necessary and the high amount of end-of-life material that you need for an efficient process. And this is, well, the schematics of the method, that in fact the flakes are wrapped into the dry reinforcements and resin is added, and then it is cured in the mold. And with this, we cooperated with a company called Krafton. They do pultrusion already over 30 years, and we found that it could be done. And also we use these parameters of this company and also the speed that are attainable with this method to investigate what are the costs and what may be profit as a function of the amount of end-of-life material that is inside. And this is a crucial parameter because the percentage, the weight percentage of end-of-life material in this new product is very important for the profitability. The more end-of-life material is getting in the profile, the better. And you can see this with these lines. And especially if you have more production lines, the profitability goes up, of course. Also, for the carbon footprint, we investigated by using the eco-calculator of USIA. Then it appears that when the amount of end-of-life material is not sufficient, so 50%, then it has a higher carbon footprint than traditional thermoset with profiles with, for instance, a foam core with a yellow picture or a hollow pultrusion profile. However, if the amount of end-of-life material increases to 70%, then the carbon footprint is the lowest of all. So again, the percentage, the weight percentage of end-of-life material is crucial. And this 70% weight percent is attainable. We also have proven that. We investigated environmental safety because there were questions whether harmful substances could leach out of the new composite, especially in infrastructural applications near canals, etc. And we investigated this with SGS, and it was not measurable, the amount of material that comes out. Although harmful substances were inside, especially old-fashioned gel coats from boats and anti-fouling for boats were inside, was analyzed, but it doesn't come out, even not when the profile is damaged. We even tested that. We got a lot of recognition and awards. We got recognition from USIA as the method being a closed loop solution. So a step further in the, well, the air categories than co-processing. And we got also a JAC Innovation Award So this is very helpful for us. We have partners for industrialization in the Netherlands that we cooperate. Protrusion company Krafton, CRC that makes the flakes, and other companies that are working on the method. We are not sitting still. We are cooperating with the Dutch Railways and also a European group for sleeper developments, so the railroad ties to make them from reused composite. And also we are developing lightweight panels, and this is a really new type of application. We do this together with VDL Fibertech Industries. Conclusions are that we, although there are promising developments in recyclable resins and infusible thermal plastics, which is very good, we still have to do sensible things with traditional thermoset composites the coming 20, 30 years as they come. We have made this reuse method. We developed this. This is a closed loop solution. We can make new composite products that are useful. We cannot make new rotor blades, but useful products, for instance, for infrastructural applications. We have shown that there is a good business case possible, also considering the market prices that can be it can be sold for, and a sufficiently low carbon footprint. We have developed this also using a design approach that is customary for composites, and we have proven it with demonstrators. And furthermore, we investigated also the environmental safetiness. So this is, well, in short, what I would like to tell you, and I thank you for your attention.
Any questions from the audience for Albert?
Yes.
Hello, Ronan from Suez. What is the volume you already recycle into this product? Is it just proof of concept, or it's now starts industrialize?
Well, it's not full scale industrially running. The problem is that there's not sufficient incentive to use the method at the moment as compared to traditional pultrusion, for instance. Although the method is possible and there is market, still we need some pooling, and that's the same problem that also the company CRC has that makes the flakes. Their business case is based on getting a gate fee from people that want to get rid of their end-of-life composite, but they also want to sell the flakes. And this is not running in a large-scale industry yet. No.
Okay, thank you.
Marcelo.
Thank you. Interesting solution. Question is, how do you define closed loop? How do UCR defines closed loop?
Closed loop, yes,
It's really a matter of definition here, because in my view, closed loop is when it comes back to the previous or original application.
Yeah, that's true. If you look at that way, then it's not closed loop. It's closed loop in the sense that you make a new composite. That's
okay.
Yeah.
And I think just to clarify what you were saying, Albert, you suggested or intimated that closed loop is structural into structural.
Yeah.
Is that?
Yeah.
That's
exactly.
something that you're using as a definition or something?
Yes, it is not a reuse in the sense that it's not using well the good mechanics of the composite again. So you really are using the mechanical properties that are still inside the composite.
Yeah, don't get me wrong. I like open loop.
Okay.
I mean, it's a matter of definitions.
Yes, you're
Only
right.
a matter of definitions.
Yeah, but that's true. Yeah.
just out of curiosity, something, if your team has been doing, or if there are other, if you're aware of other groups here in Europe that are doing this, where around freeways, interstates, roads, where you have residential housing very close, cutting the blades along the y-axis would be really nice for dampening walls.
Yeah.
Where high traffic areas. Is that being done here in Europe?
Yeah, well, at the University of Delft, we cooperate with them. There are a lot of activities going on to use larger parts of rotor blades, which is of course much better than make it first into flakes. And they are investigating not only street furniture, but also bridge structures out of rotor blades. But it's difficult to industrialize such a method, although it's higher on the R ladder, so to speak.
Yep.
Yep.
We also have 2 online questions, if you can answer.
Okay.
First one from Vasileios. What is the composition of the flakes?
The flakes are really the composite parts, so it's still a fiber reinforced piece coming from the rotor blade. I must say that when you cut the rotor blade and then shred it, a lot of dust is formed. Also because of the core materials like the foams. It used to be PVC foams, nowadays PET foams, but balsa wood also, and they disappear. So a large part of the initial weight is going away, and what remains and what we use are really fiber reinforced thermoset parts.
Okay, and another question is, what is the fiber resin content of the finished product?
Well, to make that calculation at this moment, it's difficult. At least the composition contains 70% of its weight of reused composite, and about 25% is resin, virgin resin, and 5% is virgin glass reinforcement. But of course, there's also resin already in the flakes of the reused material. So if you make the calculation with that, it may be about 50% of the total.
Okay, last one. Are there any cases as the EOL rotor blade made by polyester resin or epoxy resin?
Yeah, that's a good question. With our method, it does not matter very much or not significantly whether the rotor blade was made with epoxy resin or with polyester resin. Initially, rotor blades were made both with polyester and epoxy. I don't know what is the ratio nowadays, but I think it's tending more to epoxy using, but it's no problem. Both type of flakes will give the same type of result.
Very good. Thank you so much, Albert.
Yeah, thank you.
So our next presenter this morning, this will be Dr. Ana Teresa Macas Lima, Blades to Build Project Coordinator at the Technical University of Denmark. So welcome.
Thank you, David, and thank you, the organizers, for having our project here today, talking to you. So I will talk about Blades to Build. I mean, I've talked about this project before, but I'll just reiterate what it means. So Blades to Build is meant to be a recycle, repurpose, and reuse end-of-life wind blade composites. And we aim to build a couple pre- and co-processing demonstration plant. Okay, I mentioned earlier that there's the circular economy framework, or the R framework. And here it's represented with this arrow, as you can see. So let me guide you through it. So at the bottom, we have recovery. And recovery is really one of the lowest points of circular economy. Recovery means also a loss of the material, and it has the point of transforming the material into energy. So a lot of the incineration aspects, so co-processing can also be seen as a recovery point for circular economy. So it's the lowest of the lowest for circularity. So after that comes landfill, or below that comes landfill. Then we have recycle and recycling. You all know what it is, so I'm not going to say much about it. But the big difference between recycle and repurpose is the energy requirements. So it means that recycling requires a higher energy demand than repurpose. That's the main difference between the two. And repurpose can also mean that it's also across value chains, so it exits the closed loop aspect. So then we have remanufacturing, which is within the process. So within the processing of, for instance, making the blades, we have recovery or remanufacturing of some of the materials. And I think a great example is what Decom Blades were presenting yesterday. So that's an attempt to remanufacture the fibers. Then we have refurbish, and which is very close to repair, which in the windmill, when the wind blades would be to repair or refurbish the blade for further use. So it doesn't come out. It means that it doesn't reach the end of life point that Albert described earlier. Then we have reuse, and the reuse point means that the blade has actually been defined as end of life, so it can be reused again as windmill blade. So that's the reuse aspect. Reduce is to reduce the use or the need for some products. Rethink is to rethink some of the uses of that we manufacture some products. And refuse is actually to refuse to use some products. So when we talk about higher R's, this is very close to the definitions of, I forgot the name now. Sufficiency. Have you heard about sufficiency? And anyway, so this is just a spiel of the circular economy points and how it comes with higher demands on or trade-offs with economy actually. Anyway, so back to blades to build. And I only have 7 minutes, so I hope I can present some of the project. So for blades to build, we have the recycling of the blade and glass fiber textile scraps from the wind blade manufacturing into cement clinker co-processing as an alternative. And here we put it at R9, I would say. Our repurpose of individual materials constituents of the blades in construction products like concrete and asphalt mixtures. So here we aim to repurpose the blade into another value chain, which is the construction value chain, with minimal requirements, meaning that we will bet mostly for this track on mechanical recycling. And then we have repair of the blades with minimal refurbishment or processing for the reuse of the blades again. So this is being developed at DTU Wind, a colleague of Justine Lyon, and you will meet us again there in 1 month. Let the shameless plug in again for Justine's conference next month. So the consortium, Blades to Build, we have some universities, we have DTU, we have RWTH Aachen University, we have TU Eindhoven, and we have NTUA in Athens. Then we have a lot of industrial partners, Acciona and Holcim as the main construction players. Let me see if I'm not forgetting. No, I'm not. Eldan Recycling in Denmark. We have global. We have also PreZero here. PreZero, our partners. They are there on the back. Global GCS helps us with the communication. Renow also helps us a lot with the economy aspects and getting the go decision. Endesa in Spain, GE and LM as our wind industry representatives. So, in a nutshell, the purpose of the project is this one. As I said, we aim at the recycling or recovery route for cement co-processing, but we also would like to have this higher circularity being represented in the project. And with that in mind, we have a lot of repurpose results, and that's what I'm going to focus now in the next 5 minutes. So for repurposing some of the results, and our partners were kind enough to prepare a slide each. So bear with me while I try to walk you through some of the more recent results that we have. So updates from DTU. We have 2 main concepts for the wind turbine blade waste to replace it in cementitious materials. One is replacement and the other one reinforcement. So replacement here it is a bit cumbersome, but I'll come back to it in the next few slides. We aim to replace cement with the waste, as I said, from the mechanical processing. So the wind turbine waste that comes from the mechanical processing in 3 different forms: powder, sand, and aggregate. So different sizes of the waste. And then also as fiber reinforcement. And then we replace the different fractions of cement or mortar in particular, the different fractions into different mortar specimens, as you can see there on the right, upper right. I won't go into much more details for the sake of time. Updates from Acciona. Acciona replaces this fraction with a bigger wind turbine blade waste. As you can see, 10 millimeters, so much bigger fractions. And the preliminary results, you can see it in terms of strength on the left hand, upper left hand side there. Then from Holcim has a more comprehensive approach at the moment. They try to treat the different materials, the fines, the fibers, and the aggregates, like the distinction was done before, but into different types of end uses and different construction materials. So not only cement, but installation, mortar and concrete can be combined, but other co-processing as well, and base for pavement. So all of these other products that can come out of the cement industry. I would like to go a little bit into that approach that they have there, but I do not have time. If you have some questions, I'm happy to answer. So some results from our partners in Athens, NTUA. They also do some pyrolysis and solvolysis, and they come up with these different fibers, as you can see here. I'm happy to actually provide you the contacts of our partners if you have more questions, and if I can answer, of course. Updates from TU Eindhoven. they also look a lot into the replacement of the cement fraction or the aggregate fraction into mortar with the wind turbine blade waste. And these are again some of the preliminary results you can see here. And I'll quickly go through the next one, which is RWTH in Aachen. They look into the health aspects and the environmental aspects of the shredded material that we have. From the mechanical shredding. Some updates from Renault and Endesa. I will skip that through. They were both very key on getting us the demonstration plant, but I'll focus here on the pre-zero because these are the partners that are developing the demonstration plant in Spain, and I'm sure that they are happy to answer questions about this demonstration plant that we are building. GCS, our communication partner, and if you see Blades to Build in the LinkedIn and in some social media, it's because of them. Great job. So these are some of the project fact sheets, and I would like to leave with two main messages for this project. One is the health aspects. So there was a big hiccup in the beginning of the project because it's like Albert said with the environmental aspects, but there's also the health aspects. So to work with this shredded material can have some repercussions into the health. And our partners to work with that, to incorporate the materials or this waste stream into their lines, their product lines. It is complicated. It's not linear. We need to bypass and see if this residue waste material is actually is safe enough to be worked with. And the second one, it is about permits, environmental permits. I think it is key to be aware that we have the recycling industry is very important to deal with these aspects. And we need a little bit more support maybe from the EU or from the regional governments so that we can actually push forward this. So these are the two main messages I would like to put out. Many people are involved in this project. They are all here by name and a picture from all of us. Thank you. Questions, if I have time.
Yes, absolutely. Any questions from the audience?
Hello, Ronan Gamma from Suez again. Kind of same question about perspective for industrial way. You said you develop a pilot from 6,000 ton a year. Is it effective and it going to stay like that or grow up or develop also only in Spain and also develop other country?
I think the limit that we have is actually overestimated. So at the moment we don't have the waste to fulfill that that quota. So there's space to grow in the market, I think. I'm not sure if that answers your question.
Yeah, and about developing in other country, you develop in Spain. What is the scale to develop in other countries? Is it easy to scale up or necessitate big capex, opex?
So it's an EU project. Everything will be open in the end, unless it's some trademark from the company, of course. But some of the principles, some of the ideas will be available as the project ends, as long as it's not secret from the company.
Thank you.
Hi. Hi, thank you very much for that. I just picked up on an interesting point you made there about the hazardous properties potentially of some blades. And I think in earlier discussions, it was mentioned about shipment of waste in between countries. And if a blade is deemed as hazardous, you will not be able to ship it across country borders. So you may have treatment opportunities in Spain, but if you're producing the blade in Denmark or Northern Germany, you may not be able to move it to that facility.
It is a key aspect in our consortium because the demonstration plant is based in Spain, but the Holcim facilities, for instance, are based in France. So that's already a complication there, a border that needs to be crossed. But more than that is also the safety and safety and health regulations within the company that may not allow for the workers to work with that waste. That's the key issue that I brought up. So besides the border issue, there's also the internal issues. So we need also to guarantee that this waste is innocuous.
Ben, that's an interesting comment you bring up, and we can unpack that more over coffee in a little bit. But to dovetail on that, at least in the U.S. market with EPA and Department of Energy, the groups that are involved in those types of decision-making process, regulatory-wise, wind turbine blade material is considered inert, non-hazardous across the board. And so that's something that is really beneficial in the U.S. market, not just to move material from region to region, but demonstrating that it can be recovered quite easily. So that's kind of an interesting distinction.
I think we went to large extents to guarantee that it was health and safety approved for within the universities and within Holcim in particular. But I think Claudia yesterday brought a very good point with the other constituents of different blades that we are not aware of. And at the waste facilities, there's no trial for those, right? Everything goes into the shredder.
The hidden materials, as it were. Yeah. No, that's certainly a key discussion point. Very, very good. Thank you very much for the talk.
Thank you.
It's stimulating. I'm sure that like I said, please feel free to unpack these conversations a lot more over the coffee break. So now we have Sophia Kukura, Innovation Manager at Scottish Power. Sophia.
Thank you. Hello, everyone. My name is Sophia Kukura, and I'm Innovation Manager at Scottish Power, part of Iberdrola Group. Now, my personal specialization is on wind turbine drivetrains, which is, I guess, the next best, most expensive thing after blades. So the last 24 hours have been great learning opportunity for me, and thank you all for sharing your insights. Now I'm here today to share our own perspective as owners, operators, and as organization that has to deal with a huge amount of blades at some point. And I think my presentation will echo a lot of the points that we heard from Sandro and Marta yesterday from RWE and Renner Cycle. And I think it's really good and important to see that large operators take this topic very seriously and that we are generally in alignment. So obviously, as you can understand, we face similar amount of challenges in terms of material composition, size, and also just the volume of the blades that we have. So I'm going to touch a little bit on how can we turn some of these challenges into opportunities and some of the partnerships that we have. Okay, so Scottish Power, for those of you who don't know, is part of Iberdrola Group, one of the largest utilities worldwide, with presence in many countries in Europe and outside Europe as well. So yeah, billions of pounds worth of assets, mainly specialized in developing renewable energy projects and also in networks, in transmitting and distributing electricity. So yeah, at the moment we have more than 400 wind farms and just a number of turbines, as you see. I'm sorry for throwing a lot of numbers there, but like 15,000 turbines at the moment, and a lot of them will be more than 25 years old within this decade, plus a very, very ambitious pipeline. So at the moment we exceed 23 gigawatt, and we have much more onshore and offshore and pipeline in construction at the moment. But focusing on just the UK, where I'm based, we have, as you see, we have various wind farms across the UK, many of them clustered in Scotland because we have lots of wind there. And we have, more than 40 wind farms, which amounts to 4,000 blades, and more than half of them, will exceed their estimated lifetime of 25 plus years in the next few years. So now, we have to deal with this issue, and many of you have mentioned in your presentations about landfill bans and so on, which at the moment it's not. There's no such thing in the UK, but it is expected to come. So there will be costs associated even if we do nothing. And there might be some non-price factors allocated into the CFD scheme. So the contracts for difference that we have, where we basically gain contracts to build these projects, will potentially have some sustainability targets around them as well, which will most definitely include also recycling of wind turbine blades. So it is, of course, in our best interest to deal with this topic. And I know that a lot of you have showed photos of wind turbine blades piled in places and landfills. And this is always, for people who don't like wind energy and renewable energy in general, this is always the best bad press that they can give for our industry. I've seen a lot of headlines of like, oh, look at how many wind turbine blades are just discarded, and wind energy is not as green as we think, and so on. So I think, we're all here because we understand that this is a very important topic that we need to address, and that we want to make sure that this industry is as sustainable as possible. So scale of challenge, I know we have seen similar graphs about the commissioning projections, but this particular one speaks very close to home because it's from a report that directly references us. So this is actually quite an interesting report from Zero Waste Scotland, which is a non-profit organization based in Scotland, as the name implies. And they have done various scenarios of the commissioning for the next few decades, taking into account, obviously, the install capacity and projections. So, particularly, you see the couple of peaks in this graph, which is the number of turbines to be decommissioned. And the report references our company and another large operator in Scotland, and says, in 2037, we expect to have that many turbines from Whiteley Extension, which is one of our wind farms, and in 2042 also from Kilgalleoch and Hell Hill Extension. So, and it says that this illustrates that, the decisions made by a small number of operators can really influence the material flows that arise from the commissioning. So, we have to deal with this topic, and I guess the first thing to start from is by defining what our strategy is. Now, most companies have similar strategies in terms of circular economy, at least the companies that operate in the similar field as us, of course. So we understand that we rely on resources, and we need to develop a circularity in a business to make sure that we're more efficient, that we reduce environmental impact, that we support the local jobs and supply chain, and so on. So of course you see that there is the target of zero waste to landfill by 2030, plus 100% wind turbine blade recycling by 2030. Of course, there's an asterisk there because this is subject to commercially feasible solutions. So this generally this circularity economy strategy, affects the entire value chain. So it is the things that we can, our own products and processes, the things that we can directly affect, but also the sphere around us and the suppliers and the customers in our sphere of influence. So yeah, through defining a few targets is the first step into making sure we have some plans and processes in place that have to do with, first of all, our own organization. So how do we deal with our own stakeholder management, our data management, and so on. Product level, which maybe we're not as able to influence as we don't manufacture the wind turbines, but we contract manufacturers, so we need to work with the supply chain. And then, yeah, in terms of the process level, how do we work with others around us? And there is particular focus in our strategy, of course, in terms of partnerships and how do we close the loop and work with both suppliers, but also universities and other organizations around us. So this is one example I want to mention from like some cross-industry collaborative initiatives. So we are part of SASWIN, which is an innovation collaboration initiative launched by NCC and is delivered in partnership with Offshore Renewable Energy Catapult. Now I am aware that a lot of you have mentioned various initiatives, and it's great to see there is a lot going on in different places in the world. Hopefully some of you are part of more than one or all of them, I don't know, but hopefully there is some alignment among all these things. And if you want to be part of this, I guess I can also help you connect and link some dots there. Always happy to help out and make sure we are aligned both globally, but also in both locally, and in a more European and global context. So the purpose mainly of this innovation project is to bring together partners from across the board when it comes to the topic of wind energy and recycling. So of course, wind turbine operators like us, but also regulatory bodies, government, universities, OEMs, and so on. So basically, they operate around the three main pillars of how do we demonstrate the technology required and the supply chain to reclaim the value from the materials that are already in operation, using the lowest impact solutions, of course, and how at the same time we use sustainable both materials but also processes, and how do we then close the loop and help innovate in design. So they're doing various studies along those lines. And other projects that are commissioned through my team directly that I can mention is, we are involved in things like decision-making frameworks for wind farm life extension and decommissioning. We're doing some work on material passports. There's also a fluidized bed facility in the National Manufacturing Institute in Scotland, which I think was a partnership with Boeing that we are looking to explore and see how further we can utilize these technologies. So yeah, one of the things that obviously is, I think, has been highlighted through this work and other works is that there needs to be more transparency, especially between OEMs and owner-operators. I'm just going to show a couple of interesting results of how this consortium approaches things. Basically, they want to deal with the start of life. So where do we source our materials? The end of life, choosing the right recycling technologies, of course, but also looking at through life, how do you use alternative materials and life cycle assessment and so on to minimize the global warming potential, essentially. So they did some studies on a reference turbine, of course. I don't know how much you can generalize this, but yeah, some of the results show that it is possible to reduce the global warming potential and at the same time mass while keeping your AAP. But we are still, according to the studies, on the blue circle, which is we can reduce GWP, but we don't have full circularity. And the aim is, of course, in the future to make sure that we have sustainable materials that are recyclable and bio-based, and that we made from recycled feedstock and so on. So that's where we should aim to be doing. And I think, yeah, a lot of the things I've heard in the last 24 hours move towards that direction, which is very good. Now, I mentioned partnerships, and this is one, I guess, of the flagship things that we have as part of the Iberdrola group. So this is our Energy Loop partnerships, which was in 2022. It's an open venture between Iberdrola, so like large owner operator, and FCC Ambito, which is like a waste management company. So combine those two together, and you have a good partnership and solution to deal with wind turbine blades. So it's the first industrial scale wind turbine blade recycling plant in Europe, and it was supposed to be operational now in end of 2024, but it will be, as far as I know, beginning of 2025. So yeah, obviously this takes into account the region around that area, the wind blade recycling flow, but also how do we make sure we are in a region where we can influence green jobs and generally circular economy. Can you guess where it is? It is in Navarra. So it's very interesting that the plant presented yesterday as well is in the same region. And I think that kind of tells the story of particularly the government of Navarra and how they want to be in the forefront of innovation and circular economy. So as far as I know, they were very, very helpful in terms of like accelerating permits and so on. So they also seem to be taking this matter very seriously. Also, it is a region that has a lot of wind farms around it, a lot of old wind farms. And as someone said yesterday, there is enough blades for everyone. So I think there could be probably more facilities in Navarra. And maybe the next recycling forum, we can have it in Spain and go and take a tour in our facility and the Renner Cycling facility. But yeah, there is a large amount of blades expected to be coming from that region in Spain. I think, yeah, the estimates are 5,000 blades per year in general. And it's really important to establish also good collaborations when you have a facility like that. So we have like the support from Siemens Gamesa, manufacturer, but also from Surus, who is a specialist in like circular dismantling of industrial facilities, and they have a lot of experience in wind energy. So a lot of the things that they that from their decommissioning activities that is not supposed to be used in something else will be coming to our plant. So yes, this is basically kind of like an end-to-end solution of making sure that we study what is the input flow from the wind farms around us, and also how can we basically use the materials afterwards, and how do we best market this. Now I know that I can't remember what the capacity exactly of the plant is, but I know that the expected market share and market size that they think they're going to have is around 1,500 blades per year or so. And there are 2 shredders in the facility. One of them operates at 8 tons per hour, and the other one at 3 or 4 tons per hour. So I just want to show these pictures because they are quite nice. And thank you, Ana Teresa, for showing us all the order of ours. So obviously, if we can just take a blade and repurpose it for something else, it's very good, and that's one way to do it. But of course, with the amount of blades that I mentioned, there are that many playgrounds and other things like architectural art installations that we can have. So yeah, the next best thing is to find the right off-takers and make sure we do it in the lowest impact way as possible. So in our facility, I know that cement is one of the biggest contracts that we plan to have, the cement industry. but also other like automotive application and so on. We generally, at the moment, are focused on higher TRL technology, so like mechanical treatment, but we are open in the future to explore new opportunities. And yeah, lastly, yeah, this was one of a nice story that turning a challenge into opportunity, and we want to make sure that we are ready when the huge amount of repowering and decommissioning comes to deal with some of it, because it is also largely our own problem, but we need the help of the supply chain around us to deal with it, and the help from research institution to accelerate some of these lowest TRL technologies. And creating, good alliances, as I mentioned, is a big part of this story. Now, these are some, I think, photos from earlier in the year in the plant. So it's not a real facility until a politician with a high-vis jacket visits your plant. So this is, I think, the officials from Navarra coming to see the facility. And hopefully, like when it's operational next year, we can have more lessons learned from it. So thank you very much for listening, and I open to questions and discussing later. Coffee break.
Any questions for Sophia?
Thank you for your presentation. As an owner of wind farm, does Scottish Power also has budgeted the cost for the end of life treatment of rotor blades?
Sorry, can you repeat if we have the cost?
Does your company also have already have budget reserved for the rotor blades when they are come to the end of life or end of use stage?
The short answer is yes, because this is something that we need to deal with, and we already have some plants that we have repowered in Scotland. So we are trying to find solutions to deal with this. So yeah, the short answer is that we have some budget, but we are looking at the best solution. So at the moment we have some blades that we are still looking what to do with.
And what are these costs based on what type of treatment?
What are these costs based on? What do you mean?
Yeah, because when you make a budget, you have an idea of how these costs are composed.
Yes.
What are you needing these costs for to calculate it? So is it then the cost for landfill or already a more recycling method? What is the basis of this reservation of cost?
Yes, I guess you would look into what are the different options. Yeah, putting into landfill or also repurposing for something else and so on. So I guess minimizing the cost is one thing, but also there are other non-price factors that are taken into account. And yeah, we want to make sure that we operate as locally as possible as well. So yeah, it's a combination of things.
Yeah. Okay. Thank you.
Yes.
How do you plan to involve off-takers? Because you have shown that you have contracts with the cement production. Okay, that's state of the art, let's say. But you also have plans to go in other sectors and involve more off-takers. What are the plans? What is the strategy to involve them? Because it's not trivial. I mean,
yeah, it's not very straightforward. But yeah, there is a team of people like working at partnerships and closing the loop and bringing those things together. So I start having these discussions, and then trying to see where the needs are from other industries and fill those gaps. So yeah, I don't know if that answers your question, but it's not very straightforward, and it's also very location specific. So like yeah, in Spain you would need to obviously work with first look at your local suppliers. If there was a facility somewhere else, I guess you need to reestablish some of these relationships. So it's not very straightforward, and I don't think it's something you can copy paste very easily. And you need to define a good business model first. But yeah, I think having like Energy Loop, having the support of being part of like Iberdrola and FCC kind of like, I think helps potentially open some of these doors and discussions more easily.
Last question, Julian.
Yeah, you've got really hard questions to answer, so I'm going to add one. What is the degree of urgency within SSE to deal with that problem? Because clearly you haven't selected your solution. So I'll separate the question into when do you think you have the problem hitting you? Is it in 1 month, 1 year, 10 years? Okay. And what is the degree of urgency within SSE to deal with it? Because you need support from management to make decision, and okay, there is a budget, maybe you'll spend more, less, etc. But you have a volume to deal with. How? Yeah.
First of all, it's Scottish Power, not SSE, but I see the confusion. So
Sorry,
no worries. Well, it is at the moment an urgent topic, and it will become even more urgent in the next 5 years, like before we reach 2030, because we have a lot of quite all offshore wind farms in Scotland. So yes, there is a big urgency, and I think that also it is a priority from senior management and beyond to deal with this. So at the moment, my sustainability colleagues are working really hard to make sure we deal with this problem at scale, because it's not just one wind farm with 5 turbines. It's thousands of turbines that we need to deal with. So yeah, it is very important, and that's why I'm here as well, to learn and discuss about this.
Sophia, thank you very much. So now we have a few minutes to replenish with some food and drink. So we'll be back here in just a few more minutes at 10:45.
Ne?
Že Pepo, že Pepo, poslouchej.
To je smutné. A co máš, ty máš ten čínský, to Xiaomi? To Xiaomi, no. No, Čína, no.
Se nediv, no.
Sledovali.
Oni dělali jinde na vedlejší den celý.
No jo, no jo, no jo, no jo, Pepo, ty Xiaomi, to prostě se špiči. Halo, co je, funguje to? No tak vidíš, tak dobrý. Tak restart zvukovky.
Ale to musí do streamu teďka.
Jo.
I have one question. So as everyone makes their way back in, bring your coffee, bring your donuts, whatever. We will now hear from Mattia. She is the Sustainability Research for Impact and Economics at Tridios Investment Management. So thank you for coming.
Does this one work? Great. All right. So for those of you who have already started making your way back, thank you for that. And also thank you to the organizers for having us here. It's nice to... Closer? Oh, wow. I really hear that. Yeah, so thank you to the organizers for having a financial institution. It's really great for us to be able to learn more about this field. We're trying to grow our in-house knowledge on this topic so that we can make more informed investments. So that's our reason for joining you in these sessions. Today, I can luckily be here for the whole day. Unfortunately, yesterday I had to run off before lunch. So just so I know loosely, how many of you have heard of Triodos Bank already? Maybe a raise of hands. Okay, some, but definitely not half the room. That's always good to know, so then I know where to start with detail. Triodos Bank is a relatively small green bank. We're based here in the Netherlands, and we have several branches in other parts of Europe. So in Spain, in the UK, in Germany, and in Belgium. And we also have our investment branch that's based here in the Netherlands. A little bit about myself so that you know who is going to be telling you this story. I come from much more of an academic background before working at Triodos. So I always looked, I'm a legal researcher looking at the barriers, the legislative barriers to the circular economy transition, and usually specifically focused on Europe. So what are the additional administrative burdens that are placed on circular actors, and how can we balance that out in comparison to more traditional actors? Okay, let's see now whether I can work clicker. Oh, they fixed it today. Fantastic. So basically, first, I'll talk a little bit about impact at Triodos more broadly. So how we generally approach our vision to impact and our impact strategy. Then I will talk about our perspective from what we know at the moment about this topic. So wind turbine blade end of life, really from a resource transition perspective. And then I will give some investment examples, some clients that we already have that are putting these solutions into practice. At Triodos, we believe, oh, it's also maybe good to note that I can't see my notes here, but we believe that all money has impact, and the way that we direct that money will create the future that we want to live in. So is that future that we want to live in one where the economy is powered by fossil fuels? Is it one where we are continually mining new materials without making use of existing materials? These are all the types of considerations that we take into account. Our vision is that we want to create a prosperous life for people on a thriving planet. Now, that's a relatively short sentence, but I think there's a lot crammed in there. So what we mean by a prosperous life for people is that all people have the resources to live healthy and fulfilling lifestyles. Of course, on a thriving planet where the economy is working in collaboration with nature rather than against it, and also, of course, within planetary boundaries. The transformations, the systemic transformations that are needed for us to create that change are very complicated. They involve a lot of stakeholders and a lot of different institutions. So we've identified 5 interlinked transition themes through which we hope to create that transformative change. They are the food transition, the well-being transition, societal, resources, and energy. I think you can tell relatively easily that for today's topic, the main transitions are the energy transition and the resource transition. So of course, wind turbine blades clearly fall under the energy transition, but when we look at them from this more material perspective, it's really the resource transition that falls in. Triodos Bank has been a player in the energy transition for a very long time. We've financed one of the first commercial wind turbines right here in the Netherlands. But of course, today, our scope of the energy transition is a lot broader. So we invest in wind, solar, hydroelectric, fiber optic, and also energy storage solutions. We do all this with the goal that's outlined here in mind. So a movement away from fossil-based energy production to clean energy generation that is accessible and affordable for everyone. The way that we do this is in the 4 ways that are listed here. So firstly is through our minimum standards. This is basically the exclusion criteria that we apply to all of our investment and financing projects. With this, for example, we completely exclude the fossil fuel industry so that we're not investing there at all. And then for the sectors that we do invest in, we put in place criteria in our minimum standards for the criteria that the projects have to meet. So, for example, different certification standards that are required, or if it's a project that affects biodiversity, there's biodiversity minimum standards, and so forth. It's also good to mention that we are an impact first institution. So that means that even though we have a triple bottom line where we measure our success through profit and our impact on people and the planet, the impact part comes first, which is also why you'll hear me say the word impact several times throughout this presentation. And the third way that we do this is through transition themes. So these are the 5 that I outlined on the previous slide. And it's very good to have them here alongside the minimum standards component because they are the flip side of the minimum standards. So with the minimum standards, we try to reduce negative impact. And with the transition themes, we're really trying to steer on where we want to create positive impact and how. The last component is advocacy and change finance. So I find this a very exciting area of our work. We are, in addition to just financing change, so through the projects that we finance, we're also trying to change the financial system more broadly by changing the regulations that are in place, putting our voice into the chorus there to make regulatory changes and changes to the broader economic system. Examples of this are, for example, we're a signatory to the Fossil Fuel Non-Proliferation Treaty. We recently joined the European Right to Repair Coalition. They are working to change legislation in the consumer product space. So that's an example of our efforts there. Okay, then I wanted to use some of the brain power that's in this room and give you a dilemma to put yourself into the shoes of our investment managers. So in this case, you are tasked with evaluating a potential investment in a wind turbine manufacturer that also offers advanced recycling for wind turbine blades at their end of life. The process involves advanced pyrolysis in this case, so they've managed to scale it up to the degree where it's attractive for us. And the question to you is, what are some of the impact considerations that you would take into account to determine whether you should invest in this project? And then I'll, of course, say the ones that we would take into account. So, any thoughts?
This is audience participation time.
I think I made that clear.
Yeah. So the first thing to minimize your risk assessment on this, I'm assuming, can you get the feedstock? Can you do anything with it? And do you have a market for it? Oh, so you're assuming that a market's already there?
Return of investment, of course. But still.
7 years.
Yeah, go ahead.
Yeah, still out or not?
Yes.
Do you want mine?
It's on.
Okay. Okay, now it's working. Yeah, still I would look at my bank account. So cost.
So you're thinking of us as a very traditional bank in this instance. I hope you take some of the considerations from the previous slide into account. Anybody else?
Yeah, I would wonder what is. Huh? Is he? Yeah. Ah, it's work. Sorry. I would wonder as an investor for how to say it, sustainable solution. What is the amount of energy necessary for pyrolysis?
The amount of energy necessary and maybe the energy mix also, whether it's sourced from renewables or sourced from traditional fossil.
But especially the energy at itself that is needed for this process, which you can analyze, for instance, with a life cycle assessment.
Yeah. Yeah. Anybody else? Oh.
Yes, my question is, you mentioned only the advanced pyrolysis. Is that something that is your only focus, or are you looking at alternative test case?
That's definitely not our only focus. It's just I didn't want to make it all methods, so I wanted to use one that was a concrete example. Let me check how I'm doing on time. Okay, I better get on here. Could I switch to this mic? Yes, I could. All right, fantastic.
Okay. I'd just like to add the socio-economical aspects of the investment and the possibilities of local employment and the local industrial symbiosis in the area by applying this technology and this investment in the area.
Absolutely, fantastic. Thank you for that. Indeed, so several of the topics were brought up. Of course, there is a revenue motive that we can't do without at the moment, but some of the impact related considerations that we would take into account is, for example, what is the quality of the material that we're able to recover? So what virgin resources are we able to replace with that recovered material? We would be interested in the transport from the different facilities. We would also, in the future, I know this is largely not happening now, but we would be interested to have carbon capture be part of the process. And lastly, thinking about the energy mix that is used to power this process. So is it fully pulling from renewable sources, or is it also fossil-based sources? All right, thank you for playing along. I just wanted to hear whether a group of experts with a different background would have a different view. And the dilemma also really intends to draw the parallel between our resource transition and our energy transition. So, of course, when we're trying to stimulate the energy transition, but also trying to stimulate the resource transition, there are inherently some trade-offs there when it comes to materials. And that's what we try to remind with this quote here. So switching to renewable energy will only lead to a 55% reduction in global emissions. And the remaining 45% comes from the way we make and use products. And this use part, of course, includes how we treat or do not treat them at their end of life. As I've told before, we're much farther along in our energy narrative. Clients are much more familiar with our approach to the energy transition than to the resource transition. So this year we've come out with this vision paper in which we try to outline our approach to the resource transition, and it's very linked to the concepts from the circular economy. In this paper, we outline what global challenges around resource use we're trying to contribute to combating and how we plan to do that. So we have 3 focus areas that we use to steer this transition. And they were actually quite tricky to develop because when we talk about our other transition themes, energy or food. It's really very much one system, whereas for this one, it's resources throughout the economy, and it makes it much more difficult to have something that would be applicable to someone in the renewable energy space as to, for example, a contractor in real estate development. It's really different types of focus areas. So the three very high over focus areas that we developed are firstly, sustain and restore nature. Secondly, extend the life of products. And thirdly, prevent waste and downcycling. So it was really nice that a lot of the previous presentations already presented the R ladder, because you will see that very much reflected in these focus areas. We're trying to, wherever possible, stimulate the smaller cycles that you see on the image here, which of course require less energy and resource inputs. The bigger the cycle, the more additional energy and resources are needed. But of course, this is not a binding rule that we will only look at the smaller cycles. In the example of sectors and areas like the ones that we're discussing at this conference, obviously recycling and recovery pose enough challenges as is, that of course with these types of solutions we're open to the broader circles as well. All right. Then to zoom in a little bit on each focus area and provide an example, a client example relevant to the topic at hand for this conference. Firstly, we have sustain and restore nature. So this focus area is really all about reducing the stress on natural resources and Earth's life support systems. And the reason why we have this here in our resource transition is because I feel that when we talk about circularity in a business sense, it's very much focused on material efficiency and really looking only at the materials, whereas here we want to provide that broader connection to the environment and to nature. This mainly is relevant for our nature-based solutions investments, but I think the biggest connection to the topic at hand is when we are able to replace virgin resources with the recovered or recycled materials. All right, then extending the life of products and materials. So this is our second focus area, and this one has different applications depending on where in the supply chain you are. I would say that for recycling of wind turbines, the main topic here is really what can you do in the design phase. So can you explore alternative materials, so thermoplastics instead of thermosets. I've heard some mention of biological applications. So these are all the types of considerations that we would be interested in under this focus area. And I would say that our repowering efforts also fall under this focus area. So where is it possible with the least amount of new material inputs to repower existing projects and also to help countries meet their net zero targets. Then onto some client examples. So here we have Nordex. We have them under that focus area of extending the life of products and materials, because they are really working to improve the service life of their blades, all kinds of coating systems to work against weathering and to keep the blades in function for as long as possible. They also offer various repair and warranty packages that are attractive to us because they target that repair part of the circular economy R ladder. And we also have them because they are aiming to produce a fully recyclable blade by 2032, and they're already exploring the introduction of recycled PET foams, for example, so really working with new materials as well. Then the picture that has made it into basically every PowerPoint thus far for prevent waste and downcycling. This is the last focus area that we look at. And I think it's good to keep in mind that though we prefer to move towards downcycling wherever possible, to not downcycling wherever possible, that doesn't mean that it has to be applied to every sector. So in a lot of the applications I've heard today and yesterday, there really does need to be some level of downcycling. So where that's not avoidable, we understand that it has to be part of the solution as well. For examples, we have TPI composites. So they are really developing alternative uses for composite products from decommissioned blades at their end of life. And here I've listed some examples. recycled fiberglass yarns, construction panels, and structural flooring applications. And it doesn't mean that just because we put them under the last focus area here, that they're not contributing to, for example, extending the life of products, because with the R&D work that they're doing with other institutions, they definitely are. Then one that we've already heard mentioned several times over the course of these 2 days, Acciona. They're a Spanish renewable energy utility company. And the reason why we have them here is because back in 2022, they developed an innovative circular solution for using recycled materials from wind turbines in solar parks. So they are replacing the steel frame that's usually under the solar panel with a panel with materials that are made from the wind turbine blades. And we find this an exciting part of the narrative because they are reusing these materials have the chance to contribute to renewable energy production twice in their lifetime. And then I'm not going to expand too much more on Vestas because we heard the presentation from them yesterday, but they are definitely another client that we're proud of because of their commitments to zero waste and creating zero waste wind turbines. When we put our investments onto the R ladder, I think we, as we said, would like to be as high up wherever possible. But at the moment, this is mainly where we're hitting. So with Reduce and Redesign, we are trying to encourage both our commercial clients and our retail clients to lower their energy use and lower their consumption so that we can have less demand for energy overall. That would be the reduce part. About 20% of revenue of many of the companies that I listed comes from their efforts in repair. So that's why we've got that one. And then mainly the solutions are at the moment hitting at this recycle and recover part of the life cycle, the R ladder. All right. With that, I wanted to close it. Thank you for bearing along with me and also being willing to switch gears and look at this topic from the perspective of a financial institution. And I'm looking forward to whatever else I get to learn from the presentations that are to follow. Thank you.
Any questions for Matja?
Hi, Mattia. Thank you for your presentation. It was really interesting to hear what an impact fund considers, and thanks for sharing some of your portfolio. Are Triodos window shopping for an investment in the blade recycling space?
You mean, is that the purpose of my visit?
Yeah.
I think Triodos is very interested in the space, as you can see by the fact that we already have investments in this space. However, I am definitely not the person qualified to direct that. So really, they consult me more on the sustainability strategy around this for how we want to go about this. And I've actually heard already quite a lot of information that I'm looking forward to reporting back to my colleagues that are investment managers. But no, definitely the purpose of my visit today is not window shopping, no.
Can you say something?
I'll let them know. I'll let them know to send an investment manager next year.
But yeah, can you say something about the balance sheet of the bank and where the money comes from? Is it family offices, high net worth individuals, or where's the money coming from?
Yeah, we definitely do have high net worth individuals. We also have the retail side of the bank. So that's really just regular retail clients. But all of what you heard today is purely from our investment management section. And so there, all of these examples are simply listed equity.
And the total fund size?
On the fund side, yeah. For these investments, because they are more high risk for us. So yeah.
I was wondering the size of the fund. Is it $1 billion or $500 million or?
I'm sorry, I really can't say too much about the numbers. So I would have to look it up and get back to you. Sorry. Anyone else?
Yes.
On a non-financial aspect?
Well, yes. I would like to ask about the reuse of rotor blades. You can see that it is rather high in the air ladder on the third place, but you are not active in that area. Why is that?
Yeah, we've not found projects at the moment that we could invest in that are more on the reuse side. And we've also heard from when we've tried to gather expertise around this, that reuse for wind turbine blades specifically is not the most attractive option, simply because it's difficult to find that many reuse applications. But as a researcher that's really looking at this from more of the resource perspective, absolutely that would be a solution that when they ask me, I would get behind.
Thank you.
Yeah.
I see, thanks for the presentation. I see mainly large companies in your radar.
Yeah.
Do you also support small, medium enterprises and startups that are in the, of course, area that you are targeting?
Yeah, definitely. There is also more of that side. We finance mainly smaller companies also on our banking side. So there we will definitely see more small and medium-sized enterprises. For investment management, it's indeed only listed companies. So there will be mainly the range of companies that you saw today. But with the banking side there's definitely more startups and more smaller companies. Not for wind turbine recycling, but in other circular business models. Yeah. Anyone else, or am I out of time?
One more question from Declan.
Hi, sustainable one this time,
Thank you.
hopefully. So Triodos are an asset owner of turbines, I believe. How does sustainability feed into sort of operations of those assets? And maybe if that's something you're involved in.
No, I'm definitely not involved in that. And also, as far as I know, I don't think that we are an asset owner in that space.
Okay.
Yeah. Thank you.
Mattia, thank you very much for an impactful discussion. So next we have Florian Max, Team Lead Composites, Department of Polymer Engineering at the University of Beirut.
Perfect. Thank you for the introduction and for the invitation to this well-organized forum. Thank you for that. So I will talk about completely different, not bank, not financial aspects, but back to material topics. So I will present a case study dealing with recycling strategy of fiber reinforced composites based on Vitrimers. So what we heard yesterday in the evening, so those covalent adaptable networks and the cleavable epoxies, this also as a case study. So first I want to talk about us, what we are, where we are. We are the University of Bayreuth, located in the northern part of Bavaria, so in the middle of Germany. We are kind of a campus university founded in 1972 with 7 faculties, around 13,000 students at the moment, so not that big of a university, so medium to small university. Our network in polymer and colloid science is the Bavarian Polymer Institute, so the BPI, where we can do some synthesis, some molecular characterization, theory simulation, for example, also electron optical microscopy. We have some key labs as well for the Center of Colloids and Interfaces to have kind of mesoscale characterization, patterning surface characterization, nuclear magnetic resonance, for example. And the big technology transfer we also have with the new materials Bayreuth, short NMB, where we have some more application-related research ongoing. Our department, Polymer Engineering, is divided into 4 groups. So first, the head of department, Professor Ruckdeschel, who got the invitation and sent me. Then we have the chief engineer, senior digital expert, so a lot of digital material research ongoing. thermoplastics group, which is divided into two subgroups, the functionality thermoplastics also, which is not foamable, then the foams, and for the thermosets, the functional thermosets, and the composites, where I'm team lead for, I think now half a year. But now going on to rotor blades. So I want to quickly present you all what are our main research activities concerning recyclable materials, recyclable composites, and the transferability to rotor blades, because obviously we don't have a project running right now dealing with rotor blades, but with the materials they can be applied in rotor blades themselves. First of all, I think this chart you know very well. So the accumulated forecast of rotor blade materials to be decommissioned by 2050 in Europe. So this is another endless graph which we saw in the last couple of presentations as well. There is the motivation, or lies the motivation below or beneath to develop new materials. And I also have to go to this pyramid or hierarchy for how to recycle or how to prevent waste. So we are talking about recycling, which is kind of applied in the middle. So it's not kind of preferred, but most preferred, but also not kind of least preferred. My idea is now in this presentation to go a bit more into detail how we can reuse or prevent waste from ongoing. So in my talk, I will focus on reuse and prevention and not for recycling, to make a rotor blade or the materials of the rotor blade much more elongated in application. Therefore, I want to talk about Vitrimer resins. So Vitrimer resins, those are those kind of materials, I think, which were talked about yesterday. I guess from your side, hi. And I want to dive a little bit deeper into this topic. So I want to keep this on a more basic level because I'm not a chemist either. I studied sports technology, so I'm coming from the sports side and having to do nothing with those chemical things. I will keep it basic. So we have a thermoplastic polymer like in a water bottle, so PET. This is recyclable because we can grind it down, we can mill it, we can make some granules out of it. And after recycling and new forming, we have again a bottle. This is because we have some spaghettis in this structure. So the spaghettis, which we can see here, those are the polymer chains. They have kind of amorphous regions, crystalline regions, and due to the crystalline regions, we can tear this material apart, we can reshape it, reform it. For a more basic view, you can have the analogy to cheese. So if you melt cheese, it is getting a little bit more fluently, a little bit more lower viscosity, and if you cool it down, you have a very, very solid material again. In difference, the thermoset polymers, what we all know, it is set in rotor blades. If we take a little bit deeper look into it, we can kind of see this structure, some fibers and some thermoset polymer. This thermoset polymer consists of a hardener and an epoxy, for example. Could also be an isocyanate and polyol when we're talking about polyurethanes. So we form here a kind of a three-dimensional network. So not only more spaghettis, which are kind of lay to each other or stick to each other, but we have a three-dimensional shaped network. So there is no recycling possible, no primary recycling possible. We have seen several loss of mechanical properties when recycling or downcycling materials, but I want to focus on really primary recycling those materials without any loss of properties. You can imagine this, or the analogy hereby is an egg. If you boil an egg, it is hard and it does not get soft anymore. So this is kind of the analogy for that. So when you're talking about cross-linking or cross-linked facts to get the advantages and disadvantages out of every material, for the thermoplastics, we have high temperature and high pressures needed to form a composite. We have to set clear that I don't mean the thermosets which can be infused via PMMA, for example, those helium resins, for example. This I don't mean with it. I mean PP or PET like composites where we have granules before impregnating. Then we have, on the other hand, for thermosets, a chemical reaction. We must infiltrate the fibers with a kind of liquid state resin. In the operation for thermoplastics, we have kind of a creep tendency, and yeah, kind of compared to standard or high performance epoxies or thermosets low stiffness. On the other hand, the thermoset resins, they kind of have a higher fatigue resistant, are highly stiff, therefore also an efficiency. We have for the thermoplastic resins kind of a limited rotor blade length, whereas on the other hand side, you can use those thermosets for high moments of inertia, so we can increase the rotor blade length by setting up those materials. I want to talk a little bit more about recyclability routes for thermosets, because I think also recyclability is a bit of a topic here. We have scrap fiber reinforced plastics for mechanical recycling. Having a grinding machine, we can regrind the materials, and for instance, we get a matrix-rich powder or a fiber-rich aggregate at the end. For heating or pyrolysis, for example, also we can have a cement kiln reactor where we also have some scrap of fiber reinforced plastic material, apply heat, add fuel, for example, and what the outcome is heat, so energy and cement clinker. And on the chemical side, we have also the scrap fiber reinforced plastics as an income. Heat pressure, and we have to kind of get this in a reactor and a cyclone to get the recovered fibers, the recovered fillers, and the feedstock monomers out of it. The big disadvantage, so the duramers can only hardly be returned to primary material cycles, and the big disadvantage is the energy demand. So there was a study conducted by Gonsalves, and they said that chemical recycling is dependent on the chemical recycling route, a highly energy demanding process. Also thermal process, yeah, is kind of very, very high energy demanding. Mechanical process is the kind of best, but due to chemical recycling, we lose kind of properties, so we don't have any more primary recycling route. So sustainable matrices in the rotor blade. So what have we heard? We have heard, for example, the Arkema helium resin. So it's a thermoplastic acrylic resin. We have a thermoplastic matrix. I don't mean, to be clear, with poor reproducibility, I don't mean that it's a bad material. It's a very good material, but we have to store this material, for example, the initiator, the peroxides at minus, I don't know, 5 degrees Celsius to prevent it for reacting. The recyclamine is a cleavable epoxy. So after cleavage, we have a thermoplastic at the end. So we have also a downcycling. And the conventional non-recyclable resins, so Westlake epoxy, for example, is petroleum-based and not primary recyclable. So at the moment, we currently have no primary recycling routes of thermoset matrices possible, in my opinion, because we also only have downcycling if we try to get cleavage or the cleavable epoxies to a thermoplastic. When we grind it, we also have kind of reduced fiber length. And yeah, this is the motivation based out of the case study we developed. So the aim, therefore, is to develop a vitrimeric matrices for glass fiber, plastic composites, and the transferability into primary recycling routes or cycles. Therefore, I want to combine the recyclability of the thermoplast with the performance of a thermoset to have, at last instance, the vitrimeric resin. In principle, just a little bit of background. What is a vitrimer? How does it function? How does it work? What is the mechanism behind it? We have a flowability through a rapid covalent exchange reaction. So in principle, we have a kind of glass transition temperature, which is stated to the left-hand side or to the right-hand side from your side. We have a vitrimeric temperature. and we have the viscosity on the y-axis and the temperature on the x-axis. So first step, we are in the temperature below Tg, below the glass transition temperature. So it's dependent on the general molecular design. So how is our molecule set up? How much aromatic structures are in it, for example, and the exchange reactions have not yet started because we are below a certain activation energy. If we increase our temperature, we are in beneath or between the glass transition temperature and this vitrimeric temperature. It's kind of a rubber elastic behavior. So the free chains, they begin to move, they start to move. So mobilization of the thermostatic chains happens here. And if we go below this vitrimeric temperature, we have a kind of Arrhenius-like behavior. So we have covalent exchange reactions at a constant network density. So this network density does not change. Kind of deformation analog from thermoplastics. So above this temperature, this material behaves like thermoplastic again. We can reshape it, and we have kind of self-healing abilities in our material. So this is very important to know that with vitrimeric resins, when they are cured and we heat it above a certain temperature, those materials can be healed again. So the example now a little bit easier, the transesterification reaction between carboxylic acids and epoxides. So it's not that easy, but I will get to this point later in this talk. So when we are below this temperature, above this temperature, this vitrimeric temperature, the chemistry behind it states that we have some kind of exchange network. So this chain, which is originally located here, is suddenly exchanged, and then we have kind of another change, a chain morphology or architecture. The abstracted application for you for maybe some non-chemical guys like I am, we have some Lego parts or some modeling clay, and if we increase the temperature, we kind of can reshape our materials to new applications and can close some cracks which can occur. We tested our first study with commercially available, recyclable or reusable epoxy resins. So the reusable epoxy resins in this case are imine bonds. So the Hardener Vitrimax T130 from the company Malinda, I think located in US. It is characterized by having exchangeable imine bonds, so moldability, Arrhenius-like viscosity after a certain temperature. And we also included in our research the cleavable epoxies. So once we have a thermoset and we apply or we solve this in a slight or a light or strong acid, then we have kind of a cleaved epoxy with only linear thermoplastic chains, so no cross-linked network anymore. The hardener we use here is the recyclamine R501. So I think this is also maybe common to you because we have here some cleavable kettle linkages, which we heard about, I think, in the talks yesterday, which then have no moldability for a constant network density. We tried this with a prepreg resin, so there's no infusion involved, but we got a little bit to the prepreg route because originally it was not designed for rotor blades. This case study we developed on, how's it called, printed circuit boards. But nevertheless, this material can be transferred to any application you like, but you have to alter the used resin to reduce the viscosity. So glass fiber fabric we also used a defoamer because we have a kind of high viscosity and not a low viscosity, and we used those three resins. So the Vitrimax, which is the Vitrimer, so to say. We have the recyclamine, so the cleavable epoxy, and we have the DieHard 100S. This is kind of a common prepreg hardener for resins for prepreg applications. Some first results, we see that there is a strong influence of hardener on the network density. So we have the highest network density here within our benchmark material. By increasing the structure of our hardener, we see that our network density is getting more increased or more decreased, sorry, because this very large structure is kind of in between the epoxy resins. Also on the glass transition temperature, we can see that with our neat material or our benchmark material, we can reach up to 200 degrees Celsius as a TG, which is way more overkill than we need in the rotor blade design. So I think the Westlake IMR is like kind of around 80 to 100 degrees Celsius, and therefore we would aim also therefore to the T130, so the Vitrimer resin. So those are kind of comparable properties. We tried also mechanical recycling of this Vitrimer. So we grind the cured resin plate down, we milled it down, did 5 recycling trials. So on a hot plate, we pressed it down with a certain temperature, so over 200 degrees Celsius, and we get a solid plate at the end of our product. So this was the first plate, then it was milled down to fine powder. And after 5 recycling steps, our material looked like this. So we get a solid plate at the end with comparable mechanical properties. This is just a particle size distribution. I will skip this. We also did some chemical recycling trials of the Vitrimer. So we had some kind of diethylene triamine as solvolysis and reshaping our material, recuring at 180 degrees Celsius. We kind of get okayish results. Not the best from optical point of view, but if we look again at the thermomechanical properties, we see that the pure resin, so the pure Vitrimer, when we temper this, not only at 140 degrees reaction temperature, but 180 degrees reaction temperature, we can get an increased network density by maintaining our glass transition temperature. By grinding and hot pressing, we reach the same glass transition temperature again. So the thermomechanical properties after mechanical recycling, after grinding and compacting this again, is kind of comparable to each other. We also did chemical recycling trials of the cleavable epoxy with some kind of not that what we expected, because at the end our specimens look like this. Yeah, I think there's way much more room for improvement than we see here. So this is from our perspective, from our first trials, the resulting materials, what we have. So in conclusion, did we establish primary recycling routes? No, we didn't, but I think we can say that we understand the mechanisms behind the chemical and mechanical recycling of Vitrimers. We created scientific fundamentals for future research. We found also a limitation in application. So the future research should then therefore address the vacuum infusible resins, or resin systems, to transfer this knowledge to rotor blades, for example. Can also be attributed to kind of debonding on demand. This means if the two shells of the rotor blades are fixed together or the webs included, that we don't have to use any kind of structural adhesive, but we can use Vitrimers as an adhesive to debond on demand, so that we don't that we can simply heat up and debond, so to say. And future research can also address new materials, like not only fixed on epoxies, but polyurethanes and vitrimeric polyester. Therefore, I want to thank you for your attendance, for your attention, and we can surely connect via LinkedIn and for future discussions. And then thank you very much. So
Any
open for
questions?
questions. Yeah.
Yes. Joachim.
Hello, Niklas from Siemens Gamesa. I have a question related to the mechanical properties of Vitrimer resins. We are demanding higher properties because we are building larger and larger blades. And how do you see Vitrimer resins in that perspective? Are they able to fulfill the strict 25-year lifetime requirement?
This we don't know yet, because we haven't, as I said, are just in the beginning of research. But for the thermomechanical properties, from that standpoint, we did also some some first mechanical, not only thermomechanical, but mechanical property testing. And there they are kind of very competitive to the commercial resins. So at the moment, so this is our state of the art at the moment, which is not yet published, but I can talk a little bit for it. We can reach glass transition temperatures up to 140 degrees Celsius, and then we are way above the requirements of the roller blade with not that much enhancing the price.
Okay, thank you.
Florian, thank you very much. This is very inspiring research and very valuable. And now you had the example of PET being remelted and becoming a new bottle. This is simply not true. You need lots of additives. If you see a bottle which has been recycled 2 times, nobody would buy it. So you need to replace the antioxidant and additive package in doing that. And that leads me to the question to you. Did you use some protective chemicals like antioxidants? What's in this Vitromers?
Yeah.
We can see the black material which indicates oxidation. So what can you do on that front?
So you're quite right. So this was a little bit of placative research or placative presentation. So we didn't use any antioxidants. This was just the first trial. We heated up the materials up to 180 degrees Celsius. I don't know if there comes a little bit of I don't know if there is that much issue of oxidation. Thank you. Within 180 degrees Celsius for such a high TG temperature material, because PET is like recycled at 200, 250 and above temperature. So
maybe a suggestion, if you work under protective gas, under nitrogen, and also if you did the milling at a very high temperature to prevent breaking bonds unnecessarily.
Could be an option, yeah. But you have to also bear in mind, so I totally agree with you that one need to maybe get a little bit more antioxidants, so to get a better material out of it. But you have to also bear in mind that sorry, I lost what was the question again?
No, I mean, if you do milling and processing under protective gas, under nitrogen, for example, you prevent oxidation.
Yeah,
just as a suggestion.
Could be, yeah. Thanks for the suggestion. Yeah, could be worth to try. Yeah, indeed.
Any other questions? Florian, thank you very much for your time.
Thank you too.
I believe that I am next on the agenda. So David Morgan, Carbon Rivers, Chief Strategy Officer. It's a delight to be here. This is great because we love participating in these events, understanding what you all are accomplishing in a tremendous fashion in the area of composite and polymer composite circularability. So if you've seen me talk before, you know what's coming out. I like to have a bag of tricks in all my jacket pockets. But this is something fun. I like to, when I was a child, you have maybe something like this in grade school here in Europe or the UK. We call it show and tell. So this is part of the show and tell piece. Most of you think this is a sprayer head. It's not a sprayer head. It's a wind turbine blade. So what Carbon Rivers does, of many things, we're an advanced materials engineering firm. We came out of US DOE in East Tennessee back in 2017. And when we started Carbon Rivers, we wanted to commercialize advanced disruptive technologies. and we wanted to bring things to market that were truly impactful, not just to steal words, but things that were disruptive and causing tremendous advancement in nanotechnology, material science, et cetera. So we were approached back in 2019 by the Wind Energy Technology Office on the idea of having a funded project to do proof of concept in a batch line in Knoxville, Tennessee on wind blade recovery. So since then, it's been very successful. We've added aerospace, automotive, building material, marine, and other composite industries kind of into the mix. But this, yes, it is a sprayer head. You see it on the shelf at grocery stores in the US, but this is 20% by glass weight recover from wind blades. And then we do injection molded pieces with polypropylene for something like this. So this is there in the US market. Just as a proof of concept that actually was more popular than we expected. This is not a wind blade, but for those of you in the room who are French, this is our Arc de Triomphe. We work a lot in the marine industry, both in the US market and Japan and in other countries. So this is post-production scrap from Yamaha, one of our partners. We recovered their post-production scrap and then put this into polypropylene injection molded pieces. Of course, we can use non-virgin polymers as well, because we have capability in that space. But for their proof of concept, which this is a component on their new boats in 2025, and not only for Yamaha, but some of the other boat manufacturers wanted to adopt the same thing. So what we wanted to demonstrate to the marine space, as well as wind and aerospace and automotive, et cetera, is full circularity for all their scrap. So now they don't have to send anything to landfill. All their production scrap that's glass fiber composite waste material can be repurposed into components going into their new materials, so they don't have to depend as much on virgin materials. This is additive manufacturing, a little benchy boat. Again, this is a wind turbine blade. We recover the glass, put it into a polypropylene filament, but we work with other polymers as well, not just polypropylene. And then this is something we do in the additive manufacturing space. So I wanted to kind of show you these things, and I have samples in my other jacket pockets to show you as well, because it's really important to demonstrate not just the theory and the academic paper and the lab scale, but the commercial viability of these things. As we were talking about earlier, for investment and for financial and business wherewithal, we have to make sure that we have a feedstock, we have an offtake, we have a good business model that makes sense. All these are necessary components to solving the problem of wind blade or just composite circularity. So Carbon Rivers, like I said, is an engineering firm. We're an advanced materials engineering firm. A lot of our team came out of compounding and polymer composites, but we have, in terms of engineering disciplines, we have nuclear, material, chemical, electrical. And what we do in that space is we work a lot in metals. We work a lot in nanotechnology. We do quite a bit in the space of elastomers or lubricants, in addition to polymer composites and whatnot, coatings as well. So two main kind of showcase technologies that we've commercialized. One is the production of pristine graphene, and we'll talk about just a moment towards the end of the slideshow. And with our pristine graphene, we manufacture 1 to 3 layer mono bi tri-layer nanoflake material, defect-free. It's very different than a carbon nanotube or a graphene oxide or reduced graphene oxide material. It's pristine, so it's inert. It's not functionalized, no oxygen groups. And we produce that at commercial scale at a very, very low cost. We treat it as a commodity, because if graphene is going to have an impact materially in various industries, tires, coatings, metal alloys for transmission lines, as an example, polymer composites for lightweighting of blades, these types of things, it has to be treated as a commodity material. So we commercialized that. And then we also brought to market the idea of, not the idea, but the capability of recovery of glass fiber, carbon fiber resin systems from end-of-life materials. So a little bit about what we do in those two kind of large technology spaces. So not to belabor this point, but we all know that there's, basically 2 large options today. We can bury blades, we can incinerate or burn blades. But within moving beyond that and maturing the conversation, there's so much more in this room that we've already unpacked and discussed in that space. So what we specifically do under Glass to Glass, whenever Carbon Rivers commercializes a new technology, we wrap it up in a different silo division, and it's a subsidiary under Carbon Rivers. So Glass to Glass is a thermolysis recycling, very, very different than traditional pyrolysis. And a couple of the reasons why is it's a very low temperature reaction. We just have it in the kiln quick enough to crack the polymer. So all of you know who work with this type of science and this type of manufacturing process, you have your once you crack the polymer, you have light hydrocarbons, heavy hydrocarbons, the organics and the inorganics that come off the line. So we can kick it off with electric or natural gas, depending upon how the line is designed and built. Also on renewables as well. So it runs very well off of like a gas generated turbine or something like this, or a solar field. So we have multiple options for energy input into the system, depending upon what is needed. And then when we run the system, as I said, the polymer is cracked. Light hydrocarbons is our syngas, as you realize, that runs through the system for net positive. Heavy hydrocarbons condense into our pyrolysis oil. There you see at the bottom right. And then, of course, we extract the glass out on the top right. So you have clean, mechanically attacked glass that can go into next life cycle manufacturing. And so I'll unpack those in just a minute. So that's a 1-ton reactor that we did with the United States Department of Energy, very successful project. It was a SBIR, if you're familiar with that funding mechanism. It's kind of like the Horizon type projects you have here, a small business innovative research grant. And so we did a phase 1, a phase 2, and a phase 3 with the Wind Energy Department and DOE. So we're looking at some add-ons, so to speak, for the commercialization of this in other regions like Texas, where there's a slew of wind blade farms, as you can imagine. So a couple of things I want to mention too, specific to the glass and the resin oil, is on the glass side, there's obviously certain tolerances, whether it's going into structural or non-structural components and things like this. So a couple of things we do to minimize the degradation of the glass, which all of us who work in a pyrolysis or sovolysis type of system, we have to be aware of. You can blend the glass with virgin as one example. You can also use certain sizing chemistries as well to strengthen the glass. You can use graphene as well as another additive to strengthen the surface chemistry of the glass to get those mechanical performances you need. Or not, maybe it's a functional performance. Maybe you want UV resistance or anti-corrosion, antimicrobial qualities as well. So we have a variety of different solutions when a customer comes to us and they say, we want a glass fiber or a carbon fiber or resin system recovery, and it has to meet spec. These are the specs to go into a new material, a new part, a new component. And so we work with those, say, downstream partner customers and meet that spec so we can do proof of concept with them and then move into a commercial scalable project. So you see pictures of the glass there. We don't have contaminants in our glass based upon a lot of the glass fiber OEMs that have evaluated our material. One thing I want to mention too about the resin oil, we've been very, very successful with the resin recovery. So working with epoxies and vinyl esters and the whole family, we've been able to successfully work with companies like Arkema and others where we can recover that material and put it into next life cycle. They would do the fractionation on their side, getting the monomers to where they need to be for a new full circular economy resin system. So it's really important that we realize that that has been a major achievement in the industry. Resin recovery is ready now. It's something that has kind of eluded us kind of as an industry for a while, but now the capability of recovering the resins is certainly here. So this is kind of a big picture look at the process. We design and build these lines, these commercial lines for the glass fiber recovery because it's specific to our process. And when we do this, you see like a full circularity here. And one thing that's really important to note as well is, especially in the hierarchy of the taxonomy of the R's that we look at, when we recover materials, there's a variety of different purposes for those materials. As an example, concrete companies or groups in the infrastructure building material space says, we want to use less virgin material for, say, fibers in our concrete mix designs. We say, great, you can use less cement and you can also use less, as some of you already realized and have mentioned in the talks previous, you can use less cement and you can use less raw material or virgin material, glass fiber, going into strengthen the mechanical properties of a concrete mix design. And so those are very, very good purposes there to reduce the virgin intake and also reduce the cement, which has its own emissions footprint. So with that, customers ask us for different, say, solutions or products. When we first started with this, most of our interest was, of course, on the recovery, the separation, say, from the glue from the glass, right? The resin from the glass. And so when we were able to do that effectively, other customers said, well, it would be actually better for us if we could keep the epoxy on the glass because we have specific applications that we want to do there. So now we have more and more customers that want us to do thermoforming and compounding with the glass, with the epoxy on it, just as a shredded material. And that is a whole new market that has opened up, which is very, very fortunate and nice because that's a mechanical side, as you know. So that's less energy intensive. It's very nice because immediately you have significant offtake opportunities for volume material just at that stage before you take it into the thermal event and crack the polymer there. So we have a variety of different product offerings, we'll say, based upon what our customers want. So as an example with the shred, we all know that's a picture of what it looks like. It can go into additive manufacturing straight away. It goes into lightweighting of composite panels for marine or automotive building materials as well, which is quite nice. And so again, we're displacing virgin material. It's going into some type of concrete type of application. Then they want less cement, but they don't want to compromise the mechanicals. So that's really important for like stone and block and things like that, or just concrete mix designs. So there's many, many different types of material that just the shred can go into, not even taking it into the next step where you get the glass separated out from the resin. So here, this is just a few pictures I put together. You saw the sprayer head already. We do non-wovens, thermoplastics. I've got some samples on me if you would want to talk and look at those. But all of us know that this is a problem that's not going away. Obviously, it's just increasing. So we need scalable and regionally scalable solutions for all this now. So this is one of the reasons why it's so fantastic to have a group of people like this, because all of us together is solving the problem. And it doesn't take one company or one academic research team. It takes all of us to solve this together. So our contribution specifically is being able to, I guess, put a dent in the industry, if you will, by taking material, lowering or displacing virgin material and getting this into a variety of different applications with the groups that we work with. We started on the wind side because it was a wind-based grant that kicked this off. But since then, automotive and marine, as I've mentioned, and aerospace and building materials, glass fiber OEMs as well that we work with, have all wanted different types of solutions based upon a technology like this. So just a couple slides on the pristine graphene side. And one of the reasons why I included this is because this is a part of our Carbon Rivers portfolio. But two, there's so much we do in the wind space or in the polymer composite space that is graphene based. So a different company, Carbon Rivers Nano, that we have, like I said, 1, 2, and 3 layer material. It's inert, defect-free. It's hydrophobic material because it's not functionalized with oxygen groups. So it's a very effective nanoflakes. I have some of those as well on me. But and it's food safe, which is really great because we work with food packaging groups. And so just as an example, I know some of you have background in food packaging or you're aware of the need in that industry and even the recyclability of the polymers in that space. So we work with companies to do proof of concepts. And with that, graphene is excellent for barrier protection. It's antimicrobial and it's UV resistant. It absorbs both A and B UV. So with those types of qualities, it's really, really nice because you can cut your polymer, your PET or your PE food packaging materials down. So you're saving material costs there because you're getting boost in mechanical performance in the graphene going into the polymer. Plus you get UV resistance or absorption more specifically and barrier protection from liquid and gas impermeability, as well as, of course, your antimicrobial qualities. So these are some of the areas that we are in. As a company, again, Carbon Rivers Nano is a different division. We have CRX coatings that are our graphene-based coatings. We have CRX or CS structures, CR structures, which is going into infrastructure and building materials and things like that. We did a very interesting thing back in, this is even before we started on the wind recycling side of things. We take our pristine graphene nanoflakes, we gel spin them into ultra high molecular polyethylene, and that's really fantastic for lightweighting of armor systems, body armor, vehicles, grid hardening, building protection, things like that. So initially, we only went down that path because we wanted to demonstrate basically to the market that the graphene material is so high quality, it can go into gel spinning of ultra high molecular weight. So that kicked off a lot better than we expected. But there's so many different applications kind of in the armor and defense space because of that. So anti-fouling and foul release, or antimicrobial coatings as well that we work on, concrete and building materials, we do quite a bit. We're actually very, very surprised at how well the glass fiber recovery or the pristine graphene does in various types of concrete mix designs. So we did a project not too long ago, and we work with different countries, by the way. So with that, we took a 4,000 PSI concrete and took it to 9,600 PSI. So you're talking about early onset strength, you're talking about a hydrophobic concrete mix. Not only are you lowering natural resource water in your mix design, but you're also lowering your micro cracking and the damages to the concrete during the cure rate because you have high thermal spikes. So the graphene is great for thermal dissipation. It thermally uniformly dissipates that heat energy during your 28-day cure cycle, so you don't have micro cracking in your substrate. Therefore, you don't have to do remediation or servicing to that particular project in the future. So very, very nice there. So one of the things that we've noticed too with graphene and concrete is we're lowering cement by a lot bit larger, say, percentage than we expected. We thought that we could lower cement by 10 or 15%. We've done some concrete admixes and mix designs with our customers. We're lowering cement by 30, 35%. So that's an enormous advantage. If it's something that's in this, looking at an EPD, Environmental Product Declaration, we're looking at LCA and things like that. And so as an example, imagine doing a new wind installation, you know, offshore or onshore, and pouring your installation with the concrete that is a genuinely decarbonized concrete because you're lowering your cement and therefore your emissions by anywhere from 30 to 35%. So we're actually really surprised and impressed, as we all do research in our various capacities and roles, when we stumble upon things that works maybe better than we expected. Happy accidents, right? We do a lot in energy and electrical grid. We're contracted out for microgrids are very popular today. We're going off grid entirely. And so pristine graphene going into super caps, ultra caps, different grid hardening systems or upgrade systems, working with one of the national labs right now on a very, very neat project where we're able to use the pristine graphene in copper and aluminum extruded lines and looking at pretty decent jumps in conductivity as compared to copper, and as well lowering resistivity in those lines. So again, imagine an offshore wind installation with graphene transmission lines and tremendously lowering your transmission loss going from offshore. So these are the types of things we're trying to work on for industry. In essence, like solve problems before they become real. So one of the things I think we would all agree is when the first wind blades went up, there wasn't a significant amount of thought on how to decommission and effectively, you know, repurpose or recover or reuse or whatever the word we want to use is these, you know, large installations. Now it's kind of on our mind every single day. So what we're trying to do as Carbon Rivers is think through when it comes to grid or when it comes to infrastructure or when it comes to, you know, say coatings in the marine space, how can we provide solutions to help industry needs long before they even are on the horizon? We do a lot in performance tires and elastomers. If you're familiar with 6-PPD as a toxic agent in elastomer chemistry, it's anti-ozone, and so what happens is it helps the resistance of decay in tires environmentally. So unfortunately it's a very toxic agent, and EPA in particular and other groups are really spearheading a phased out approach for 6-PPD and tire chemistry. So we've been able to discover through a lot of research with third-party labs and with other groups that are intimately involved with the global tire manufacturing industry that graphene is the only non-toxic agent that helps to lower 6-PPD in a tire chemistry. That's enormous, and we're excited about supporting that project. Even with PFAS in textiles and fabrics and household cleaning items. PFAS, as we all know, or many of us probably know, is water resistant, is chemical resistant, is it's going into fabrics and household items for the functionality in essence. So graphene is hydrophobic, it is fire resistant, excuse me, it is chemical resistant, just like PFAS is. So working on two different projects, if you will. On the manufacturing side, instead of PFAS going into certain industry applications, using graphene to replace that, almost as a one-to-one. And then, but once it's already in the environment and has to be remediated, then that's obviously a problem. So working with companies on filtration systems, on being able to get out arsenic, mercury, PFAS, other types of really bad materials, nanometals and whatnot, desalination. So using graphene as a filtration because it is a really effective nanomaterial. So these are when we all wake up every day. Hopefully we love our job so much that we are living, again, impactfully, to use that word. We're trying to make differences in each of our industries. And so being able to help with remediation of environmental challenges, or being able to help with the extension of life of materials is something that we try to do on a daily basis at Carbon Rivers there in Knoxville, Tennessee. One of the things that projects that really gets me excited is looking at the idea of graphene infused polymer composites for blade designs. So just imagine a lightweight blade, which in the industry everyone knows is more and more of a necessity. Having a lightweight blade, ultimately cutting out your resin system by 15 or 20% in that blade design, but also having UV resistance, anti-corrosion, anti-abrasion, hydrophobic type qualities within the actual design of the blade. So right now we're doing kind of external solutions with blade designs. We're putting a product or a coating or a film or an elastomer or something like that to help with leading edge. Imagine with me, if you will, being able to do that in the actual blade design itself, the efficiencies. And if you're increasing the life of a blade by 10, 20, 30% because of the mechanical increase of the graphene and the light weighting, so it's under less fatigue all the time, then that would be an enormous benefit to the wind industry. So these are some of the things we work on at Carbon Rivers. I thank you for your attention, and let me know if you have any questions. Albert?
Yeah, thank you, David, for your presentation. I was curious about this carbon nano graphene. How can you use it as, is it a kind of an additive that you can compound into a polymer?
Yes, absolutely. So we would put this into a resin system. We'd put this in a variety of different coating matrices. So we can disperse, we can do master batches. It's just a nanoflake, right? Inert material, food safe. It's quite nice. Carry around in your pocket in the airport. But we can provide it as a bulk powder, or we can provide it as a dispersion, or we can provide it as master batch, just depending upon what groups want to use with it. We're working with some of the resin companies that some of you mentioned in your presentation now on highly conductive thermal dissipative resin systems and increasing the mechanicals, of course. But that's very, very interesting. I do have, again, in my pocket, one of them. We compound quite a bit at Carbon Rivers. So this is graphene PEEK, and this is graphene PP. So it works very, very well in so many different polymers.
Thank you.
David.
Yes.
Thanks for the presentation. So I wanted to ask you about the 1,000 blades that you processed last year. Was it 2023? Yep. So you were getting fiber out of that, and so you had what, 3,000 tons of fiber, maybe something?
So the blades, these are, say, old blades that are anywhere from 6.5 to 8 metric tons of material, kind of the first generation that are coming. Probably 15-20% of that was graveyards in the US, where a lot of the pictures that we've seen, right, that is very common. Groups contract us out, so we take those graveyard blades, we shred them down, and then we recover the material for our different products that customers want. And then we also do repowers as well. We probably did 6 repowers last year.
Yeah. So my question is where did that fiber go? I mean, so when you sold it out, the glass fiber and everything like that, how'd you sell it, and who'd you sell it to?
So I can't say under NDA who I sold it to, but
just the
industry. Yeah, building material and infrastructure are the two that want it the most right now.
So did you sell it as a fiber itself, or chopped fiber?
As a shred. as a shred.
Okay.
And then on the recovered glass, you saw that clean, pristine glass. That's going into projects for looking at working at a couple companies right now globally that want to do a continuous filament, which is another great project to be excited about. Just like with McKean and what they're doing with 3B, doing a continuous filament that's fully recovered material. You have, of course, going into, the kilns with glass fiber OEMs. So those, we have, again, the different product types that companies want. What by far we're moving the most of is the mechanical downsized portion. And then we're doing proof of concept on filaments and things like that in the next stage.
And then, so when you did that 1,000 blades, which is, let's say 5,000 tons of material.
Almost all of it went to that was mechanical. Almost all of that went to building material and infrastructure.
And did you do that in your lab there, or how did you?
No,
how
we
did you
have
prioritize that?
great. We had a 400-acre property, Department of Energy transferred to us
Oh.
for the purpose of scaling up this material. So that was, we have a rail, barge, and truck access. So it's a really nice 400-acre property.
And did you pyrolyze all that then?
No,
Or
no,
for
no,
all-
shred.
Oh,
for those,
okay.
yep.
All right,
And
all
then the 1 metric ton system you saw in
Yeah.
that picture, that's in Knoxville.
Okay.
We have 2 online questions. How are you able to replace cement? Cement is a binder. Is graphene a binder?
Is it a what? The last word?
Is graphene a binder? Binder, sorry.
Okay, no, I see what you're saying. So what the graphene does specifically is it goes into kind of the pores of concrete to increase the mechanicals. We can do a graphene conference in the future, but we've got some really great microscopy on how the graphene goes into the fissures of cracks and fills those quite nicely.
Okay, and another one. Do you pyrolyze the wall rotor blade parts, including balsa wood and foam, or do you sort it out before the process?
So the foam and the balsa, which is kind of a common constituent part that we talk about, that goes into the thermal process. Yes, and that is burned. That would be a part of the material that we capture for going into either syngas that goes recirculates, and then it's part of the hydrocarbon process. Very good. Thank you for your time. For our next presentation, we have Niels Ludwig, Senior Engineer, Rotor Blades Department at Fraunhofer, and he will be virtual. And then we also have Professor Dr. Martin Wittmeyer, Director, Institute of Energy, Recycling, and Environmental Protection at Bremen University of Applied Sciences.
No. Now you see my video. Hello, everybody.
Hello.
Yeah. Do you see my presentation or my screen? I have to ask.
We see neither at this point. Just the presentation.
The presentation you see?
Now we see the screen.
I see the screen. I have to check why. No, normally you see the presentation. Is it okay?
Yes.
Yes, okay, fine. Yeah, Niels Ludwig, my name, from Fraunhofer IWIS and Research Institute. I say some words before. Welcome to you. Welcome to the really interesting event. Some of the arguments what I tell you, we heard it yesterday and today. Yeah, and at first I have to excuse Professor Wittmeyer. He is ill and laying at home with a COVID infect, and so he cannot be in the audience and also not online. And I take over some of his slides and implement it in my presentation and try to explain you what is his topics in the project. Okay, have to check how does it function. The next slides. You see the next slide? Sorry for asking.
Yes, we can see fine.
Okay, fine. Yeah, Fraunhofer IWIS. We are a German research institute, have 76 locations all over Germany, over 30,000 employees, and every institute have its own point for the research. We as Fraunhofer IWIS are in the wind industry and especially for rotor blades. And yeah, we are split our budget. It's roughly 30% are public funding research projects where we doing for with the industry together. Then 30% are financial through base funding, means our buildings, our staff, which are not the engineers, the administration and something else, are base funded, and roughly 30% we get contracts directly with the industry. As someone of the industry have a question mark, yes, we are can say, okay, we are make a contract and directly face to face together. It's a little bit other topic as the public fundings, what's more open about this. Okay, now coming to Fraunhofer IWIS. I'm sitting in this nice building, what looks a little bit like a rotor blade. We are located in Bremerhaven, directly on the Weser River, what you see on the right side. And we are main focused about rotor blade testing. Rotor blade testing is made in the halls beside these white and brown holes, big holes, 70 meter and 90 meter. And our biggest test facility is the outside test rig, what you cannot see at the moment. It's for rotor blades more than 115 meter up to roughly 140 meter. And our activities is not only rotor blade testing. This is what we starting in 2009, building the holes, the rotor blade alloy holes, then the engineering building, then starting to also with wind measurement. The leader buoy in the offshore, also support structure, a test center what we made. Then we have a test facility for the hubs and the gearboxes and generators there in the so-called Dynalab. And then it's one of the important things, 2016, we are opened the Blade Maker Center, where we have an own mold, a rotor blade mold, and we are able to can produce rotor blade parts and special kind of things. Means we have a big lab what looks like a rotor blade manufacturing facility where we can prove new production methods, new materials, and also starting our recycling strategies. Means that we can build some rotor blade parts or rotor blades to cut it afterwards in pieces and shred it and do all the things what we discussed now. Okay, the other things is research word turbine, large bearing test, and the hydrogen lab is not the main focus for today. Yeah, what I want to say a little bit about an agenda is the concept of selective dismantling. This is for us an high value point. Then the selective dismantling of the rotor blades, separation of the sandwich material. This was the question to David at last time because we are separated. Obtaining the glass fibers also by pyrolysis and reuse of the obtained material and at least an outlook. As we start, okay, cutting through a rotor blade. There we have sandwich material there in the shell. What you see here is more in the tip is PET foam, also in the shear webs. And the spar caps, what you see here in the dark green area, it's pure glass fiber with resin. And if you get a mix of material, what we use in rotor blades, then we have roughly 60% of the weight is glass fiber. The most is glass fiber in the blade. Then a little bit in weight is balsa wood and foam, and roughly 30% resin. This is why we are thinking about, okay, the most material what we have in the blade is the glass fiber, how we can deal this. And the most expensive material what is there is the foam material and the balsa wood. Okay, a little bit of resin, but it's maybe more hard to recover it. But we are focused in our projects for the glass and the sandwich material. As we're thinking on this end of life rotor blade, we cut it in pieces. Means only cut it in pieces and separate the sandwich structure. This have to be shredded to separate the balsa wood, the foam. From the balsa wood, maybe we can make isolation nets. And for the foam, as we have separated in PVC and PET, you have to think about that the old blades up to 10, 15 years ago was produced by balsa wood and PVC foam. The newer blades starting with balsa wood and PET. But this we had to sort it out because the recovery issues is different. And the idea is to take the thick laminate, full flange laminate, 100 millimeter thick full laminate, and the spar caps, the pure glass material, getting to the pyrolysis or maybe solvolysis and recover the glass fiber. And the question mark is what we can do with the glass fiber. Okay, mill it down and use it for filling material, for adhesive or in the concrete, or can use the glass fiber for remelting to make foam glass, isolation material, or new glass roofing. For this sort, I get you some introduction about what we are doing for. Means that we are say, okay, in the project, we call it Revert. It's starting, hopefully starting next year. There we are intend to make an incoming control of the old rotor blades. The old rotor blades, what are dismantled, are not well known what is in. They are 25 years old and longer. The companies who produce these rotor blades are maybe not exist. And 25 years ago, the production of the rotor blade was very handy, very, we use the resin in this day, this type, and the next half a year, maybe another resin, or the foam was different. Also the areas where the foam and the resin is, the foam and the balsa wood located is sometimes not known. This is why we are want to develop an industrial-based dismantling and compressive with a starting incoming control. Here you see a picture. It's quite easy. Okay, we are blow a little bit hot air in and get with a thermal camera on the surface, and then you can directly see where is balsa wood, where is foam. Here in this example picture, the red areas is balsa wood, and the green area is the PT foam. It was easy because our blade was not colored, but also with a painted blade, it's functional. The blue ones are full laminate, pure laminate, so you can directly see where is the areas. Yeah, dismantling of the rotor blades is maybe a challenge, especially we are thinking about thick blades. You see it on the yard. There's quite difficult then to sorting out the areas. Next topic is separation of the sandwich. Here you see the foam and the balsa wood separation, and the last part is batch pyrolysis, and there is the batch pyrolysis without the sandwich material, pure glass laminate going through a batch pyrolysis to get with a no energy the glass fiber back. Okay, coming for the dismantling. Yeah, after the incoming control, and meaning not only thermographic image, means also that we are try to find out which sort of resin we have, because this could be help us by the pyrolysis to optimize this. From this picture, by a computer program, we have visualized the cutting edges on the blade. Here seen by non-color, not painted blade, to have a little bit more view on this. And then afterwards, we have visualized the cutting lines, cutting the rotor blade parts by a semi-automatic cutting area, shown this with the robotic arm. We have with our Blade Maker Center the possibility fully automated producing blades, also then fully automated dismantling the blades. Yeah, what we do today, maybe we see it in the presentations before. We had cutting the blades in pieces, in some big pieces there on the yard, transported then to a facility to cut it in smaller parts, then shredded it and bring this shredded part in the cement killing process. This is what we do in Germany by the company Nielsen. These pictures come from Nielsen, how they do it, but we are not recover any kind of material. We use the material for burning and use the ash of the material for the cement killings. This is the way what we do in Germany, but we looking for another way. Another way is that we are only shredded the foam material, and by a swimming sink method means you put this shredded material in a water base and then take away the swimming balsa wood on foam parts, and then especially on the balsa wood, put it in a refiner and made a wooden mat on it. Wooden mat you see in the picture here below. On the right side for fiber isolation is 100% balsa wood with some glue in between, or we put wood foam on it for isolation, for the isolation there. It makes another Fraunhofer institution. As we have the material there, we can really get a comprehensive isolation material for the building industry. And on the bottom is a laminate plank, what is pressed from balsa wood and some of the glue to reuse it also in the building industry. We see some more slides about this. Yeah, what we do with the glass fiber. The glass fiber, we make it in first trials, means the batch pyrolysis, a closed pyrolysis, closing the parts, the big parts, not shredded, putting in an oven without atmosphere, with a long time pyrolysis, and get out the pure glass and get out the oil. And in the process, the intention that the gas, what is getting there, to use the gas for steering the process. How does it looks in the project? This is from Professor Wittmeier, Bio ut Lede. This is second company what they have. They are producing at the moment a reactor, a two-chamber reactor. You see here in the picture the two chambers where we can put the rotor blades in, the rotor blade parts in. For better illustration, we are used here the full parts, but in the project will be only the full laminate there. And in a quite long time pyrolysis, we use the heated, what we need for the first chamber, to bring it then in the second chamber to minimize the energy in. And the first calculations seems that we get a positive character of energy. That means that the process itself need no outside energy. And you see here how long we are steering there. The synthesis gas getting higher and higher. And after 7 hours, we had a quite high pyrolysis chamber temperature, and we had a high amount of pyrolysis gas, what we used then afterwards for during the process. Yeah, the obtained pyrolysis oil depends mostly on the resin what we have in the parts. This is why we want to check the resin before that we have rotor blades part with the same resin amount, means epoxy or polyester resin, to get an pure pyrolysis oil, what then the chemical industry can use again. Here's some peaks what is in the pyrolysis oil, and we find these ingredients are quite different for different resins what pyrolysis. Okay, what we can do afterwards, there, we see in the industry that maybe what I explain the parts from the cement clinker on the picture 3. Picture 1 is the Megawood Novotec terrace planks from the balsa wood. Also a very interesting project is from Axionia, this solar photovoltaic plant beams. And yeah, as we get them a pure glass from the pyrolysis, then there is the tendency more and more from the glass supplier to remelt this glass. And get a new recovered glass sort and bring it back to the rotor blade industry. And we have like a recycled glass with amount of 5 to 10% lower contents technical issues, but anyhow good for producing rotor blades again. This is in a stage of research, but we are getting more and more question about this. Can you deliver us a high amount of glass material for remelting processes there? Yeah, some words about the outlook on this. Today we have in wind turbines 80 to 90% from the whole wind turbine is recyclable. It's only the blades, the part. Have to know that we have the topic for the blades, but for the whole wind turbine, it's not this big issue. As we see short term with the next projects and what we learned in this yesterday and today, we are using various processes at such pyrolysis, and the glass in the end can be reused by melting or other applications. In midterm, we are intend to reuse also the sandwich materials as we separated before. And long-term goal is to fully reuse all the rotor blade materials and also carbon fiber. Means all rotor blade material mean the glass fiber, also the sandwich material. It makes not really sense, but as we see in the balsa wood, we can make in balsa wood foam on it and reuse it instead of the foam. And the question mark is what we do with the resin, but we see some answers to reuse also the resin on it. Yeah, have to see. Thank you. And it's getting a little bit faster, but maybe we are a little bit in time hurry, and so open for question, please.
Does anyone have any questions for Niels?
Yes, Niels, this is Albert den Bussen. I have a question for you about this recovered glass that you want to supply to a glass fiber producer for remelting. Did you already try this?
Yes, in 2 research projects we tried. not by ourselves because we cannot remelted glass. But we tried with a smaller amount of material there, and it seems that we have a quite clean material. We need quite clean material. This is why we cannot get the glass away with some pollution inside. This is one point what we have to solve.
Yeah, I can imagine. I worked in the glass fiber manufacturing industry, and impurities can be catastrophic for the spinning process.
Yes.
So
Yes.
I wonder if you can manage to make it so pure that you really can supply it as a raw material again for remelting.
Yeah, the purity is the kind of what you bring in the pyrolysis oven. By the pyrolysis, you have to be a pure glass material there. Full laminate means the spar caps, the flange material. There's no other material inside. Especially there have to be no metal inside or something else.
Yeah, sure.
And we have the aim could well be, this is in discussion, we have to sort out the glass sorts itself. But this is maybe it's not the most content. It's the contamination of the glass that we have to sort it out before. This is why we are not put the whole parts of rotor blades in the pyrolysis, only the full laminate. And full laminate is normally no other ingredients than the glass and the resin itself.
Yeah. Thank you.
Yeah, welcome.
No other questions? Niels, thank you very much for your time and your presentation.
Welcome. Yeah. Thank you. If there are other questions, you can write me or give me an announcement there.
Thank you very much. So now we have Johannes Engels, Director of Strategic Sales and Marketing at Kios Titan.
Thank you. I hope the presentation will be up there. Good. I'll start already. We are Kios Titan, and we recycle thermoset material into new building materials, into new products. The company has already been doing that with Bakelite like 12 years ago, trying to make new products out of that. It is so successful actually that they used up all the Bakelite in Europe in a couple of years. And then moving to other thermoset materials was quite a challenge because there's other aspects that come along. And that's been the journey for the last few years, actually making that possible. And we're now at the step where we're actually already doing this and scaling up. I'm Johannes Engels. I'm responsible for the commercial side of the business, and I'm going to tell you today about what we're doing. So the process which we're following is we take thermoset materials. You see that on the left-hand side, for instance, from wind blades, but not solely from wind blades. We can take any thermoset materials from polyester pipelines, from hulls of boats, from all other kinds of sources. We then grind those. We sort them. That's an important thing. So we have all kinds of different sizes of materials, from dust size up to certain fibers and granules of a certain size. And we can make different recipes from that, depending on the needs of the products that we're making. We mix those then, and we coat them finally with a binder. So each little granule, each little dust particle is coated, and then it's pressed into a mold to make new products. The products that we make can actually replace hardwood, can replace concrete, can replace cast iron. So all kinds of energy intensive or scarce materials can be replaced. And the products that we make are for the construction and the infrastructure industry. For instance, planks, beams, poles, but also a little more complex materials like hydrant wells, for instance, that we're making. And maybe to make that a little bit more practical, this is what that looks like. So you see on the top left-hand side, you see, so for instance, pipes or wind blades, we can take them in transportable size chunks, so a couple of meters. We can have them pre-dimensionized by an external party, and they come in the chunks that you see on the left. We then grind them ourselves, which you see in the top middle, to a mix of different kinds of granules. We then have our own patented machine on the top right, where we actually do the combination of these granules with the binder that we produce, that we make around it. On the top left-hand side, you see then the mold, which is under a press. And on the bottom right, you see actually, in this case, the hydrant well coming out of the mold. And on the bottom right-hand side, you see this hydrant well. So this is what you see in your pavement. You walk over it, you don't realize there's a whole thing underneath actually. But this used to be made out of cast iron, not very environmentally friendly, not very energy friendly, and can now be replaced by recycling thermoset materials into almost a continuous life cycle. Because that's the great thing about this. This is 100% thermoset materials. It's the thermoset materials you recycle, putting it in, coating it with, in our case, a polyurethane binder. So after this, maybe in 40 years' time, has reached the end of life, we throw it into our grinder again and we do the whole thing again. So that's the very nice circularity about this. In this, and by doing it in this way, we can actually avoid landfilling waste. So not only do those wind blades, do those pipes, do those boat hulls not go into landfilling waste, also the products made out of those don't go into that, because they can also be, again, recycled at the end of their lives. It's very energy efficient. We don't put any heat or whatever in it. It's just a simple press, which you put it under, you then lock the mold, you leave it to cure. No waste gases that are in this production process. And like I said, we can replace scarce raw materials or raw materials that are quite energy intensive. And with that, we actually have sort of the dot on the horizon to become the go-to standard for the circular construction industry. If you look at all the thermoset material that's out there, and by using all of this to make a new building material out of it, you can actually have something that replaces the go-to materials that we have now, the hardwood, the concrete, the cast iron. One of the caveats is that we have to be aware of not mixing, for instance, thermoset and thermoplastic materials into what we're taking in. So that's one of the things with all the new developments that I think also as an industry we have to be aware of, that we can also make it more difficult for ourselves by making the blades more complex, for instance. We ourselves, we've started in the Netherlands, in the south of the Netherlands. Currently, we have a production facility of 1,000 tons per year. And with the beginning of next year, we're ramping that up to 10,000 tons a year. Our aim is in 2 years' time to start opening a new production facilities. Right now, we're looking at potentially the middle of France. The reason why is that we see as sort of an optimal catchment circle, a circle with a diameter of about 200, 300 kilometers. First of all, because of the amount of thermoset material available, wind blades, for instance, that are available, boat hulls, etc. But also the CO2 footprint of actually transporting all of this material. So it doesn't make sense to drag a wind blade from Denmark all the way to Spain, let alone all the legislation that we've already talked about. And because this is so scalable, and because with 2 production lines, you can actually make this efficient in a production location, we don't see the benefit of centralizing all of this in one big location. But once you've reached the critical mass, you can open a new factory somewhere else. our dream is actually that this will become the new production material of the future. We've called it composite. So it's our thermoset granules coated with a thin layer of binder, which actually creates this new material that you can press into almost any mold. You can't, of course, make the bonnet of a new race car out of it. But I think if you look at the construction industry, if you look at the infrastructure industry, poles, planks, beams, the hydrant wells that we talked about, all kinds of materials are very viable doing this. And the nice thing is that it's actually sort of taking this to a very concrete step where we're making a very concrete product out of it. So we're not only producing the fibers, we're only producing the granules. We're taking this to the step where we actually make the products. And that's where we come into our collaboration. Because we do this a lot together with our partners in the supply chain. Right now, we actually have deals with partners who supply us with their waste material. We process this and we make products that they want and give it back and sell it back to them. So for instance, contractors who have water pipelines, we take them on board, we shred them, and we make them into these hydrant wells, for instance. But you can also think about interiors of trains, which can be turned into railway sleepers. So actually having a deal with the party that gives it to you and selling the products back to them. So that's how we actually look at the collaboration in this field. But also this collaboration that is needed goes further than just this. I think what we've been talking about for these 2 days here is that there's also collaboration needed in the whole field, where we know what is going into these blades, for instance, that we have openness in these passports, for instance, that we know what all the other methods of recycling thermosets are, that there are different ways of doing this, that reclaiming fibers can be a good thing, but also for those that you can't reclaim, there's, for instance, this mechanical way of recycling. So in that sense, we've heard it a lot. There's enough blades for everyone. I would say there's enough thermoset for everyone because it's broader than just the blades. And in that sense, I see a very bright future actually of recycling thermoset and less turning this into waste and more turning this into a valuable new resource. So thank you very much and open to questions.
Yes, thank you. Very impressive presentation. I do have a few questions. You said you were pressing in the mold without heat.
Yeah.
Can you tell us roughly what the curing time will be then per piece in a mold?
That depends on what you're using, and we're using polyurethane, so that comes in all kinds of sizes. So depending on your production process, you can choose what fits your process.
Can you be a little more specific?
Well, I mean, yes and no, because polyurethane, you can get it in a variant that sets within seconds, and you can get it in a variant that sets within tens of minutes. So depending on your production process, you choose the one that fits your production process.
Okay, to be a little more specific then from my side, we are using polyurethane resins and we know exactly what temperatures we need to get what cure times. So there is a relationship. This is why I'm stunned when you say you have no heat in the process. So you must be talking hours at potentially.
No, we're not. No.
Okay. Did you mention when you have, for instance, let's stick with wind blades, I guess that's the theme of this forum. The fillers that are in the wind blade, do you leave everything in or do you sort out the famous PUR or balsa wood, stuff like that? Or you leave it in the mix? And then
any of the thermoset materials or carbon fibers we can leave in, but the other material needs to be taken out.
So most of the metal is already taken out because it's too valuable anyway when you, when you get it. And then, yeah, any PVC or balsa wood needs to be taken out. PVC especially is not acceptable in our process because it's a thermoplastic. But balsa wood, we can accept a little bit of contamination in there because it gets coated and doesn't disrupt the process.
Okay, all right. Now, do you have a business case that shows green numbers or that it's profitable on a large scale? I mean, you said it's fully scalable. That's good.
Yes, and our investors think so as well. So we've, I've not mentioned it, it's been on all the scale, on all the slides, but we've also received a grant from the European Union, from the Just Transition Fund. And we also have investors that have invested in this to make this possible, our scale up from the 1,000 tons that we have right now to the 10,000 tons next year.
Okay. I forgot one question earlier when I was talking about the resin.
Yeah.
Can you give us a rough indication of the percentage by weight of the resin versus the material?
Around 30%.
Okay, thank you.
Yes, I have a question. So, you said PVC, PET needs to be sorted out. So where does it go? I mean, so you basically are selecting the parts that you can use in your process, but what happens like to the rest of the blade? You know, because you have to discard it somewhere or somebody has to take care of it.
Yeah.
And then the other question is, I was a bit puzzled when you said, okay, I have this part, you know, replacing cast iron. I have a soft spot for cast iron because I'm from the metal industry originally. So, but I mean, cars are running over that, right? Or bicycles or whatsoever. So, isn't there an issue with like abbreviation or like abbreviation? What's a? I have problems too. Yeah, exactly that one. And and then microplastics. So, like, did you investigate that? What's the impact of that? That would be interesting.
Yeah. In terms of the other waste, we're right now we've not fully focused on wind blades in the sense that we've taken a few on board and processed them, but we've not optimized our process for what we're going to do with, for instance, the PVC and that. So that's one of the things that we need to look at. We don't have that issue, for instance, with the pipes that we're getting into. In terms of the durability of this, we've had these stress tests in an institute, and the weights that are put on by lorries, for instance, driving over these, and it actually is within all the limits of what is required for these materials, for these products. Did I forget a question?
But yeah, but no, this is well, okay, that are loads, you know, if you have a lorry driving over it, so that means it's just loads. But you know, over time, like, you know, you said it's sitting there like for 20, 30 years. So what happens if, you know, tires run over it like for 20, 30 years? That was my question.
Yeah, no, I realized, and I think it's come up a lot. And I think it's something that in general, if I look at what all of us are doing with thermoset material, is something that may need to be looked at. What is interesting, if you look at it from the other way, if you look at studies on microplastics in water, and they're being traced to where they come from, all of them are traced to thermoplastic materials, and none of them are traced to thermoset materials. So that, I think, can give us a little bit of confidence that these are not the kind of materials that contribute greatly, maybe at all, to microplastics in the environment.
Yeah. Hello. So maybe it's a stupid question, but you mentioned a patent.
Yeah.
What is actually patented, if you can tell us? Is the recipe or the technology you use for mixing and to create the recipe?
It's the technology of the mixing machine.
Is the technology of the mixing machine?
Yeah, yeah.
Okay, thanks a lot.
Okay.
I have one more question. Ronan Germer from Suez.
Very nice presentation. Excited about seeing you in France because I'm based in France. But one question about the gate fee. Do you have an idea about what does it cost to give you the materials?
Yeah, it's something that's come up as well in the last 2 days, the gate fee. Right now, it's quite varying. For instance, in the Netherlands, we've heard it before. Companies are allowed to landfill blades if they have to spend more than 200 euros per ton to do something with it. That means automatically that's a cap on the gate fee. We've also heard 500 to 1,000 euros that are being offered in different places in Europe. Our business case is completely positive without any gate fee at all. We'll take it, don't get me wrong, but we don't need it necessarily if in the future these things change.
You mean you take it for free?
Well, if in the end it's necessary, then we are still positive. Our business case is positive if we take it for free. If someone comes along and offers us something, someone else comes along and wants it for free, I know which one I'll choose.
Hi, it's Ben Lester here from the UK. Obviously, we've got our own issues of accessing European treatment facilities. So any treatment facility we'd like to use in Europe would need to have evidence that it's a recovery process as approved by the environmental permit. Is that something that you can provide? And therefore we can look to ship, we're supporting the UK wind industry by repowering, and we've got a turbine processing plant in Glasgow. And we're looking for, recovery processes to access. So
I think we'd have to look into that in more detail to exactly know what kind of things you're looking for, but we can get in touch and see what's necessary.
Okay, thank you.
Right, thank you.
If there are no other questions, Johannes, thank you very much.
Thank you.
So now we have lunch. Hope everyone is ready to engage conversation over lunch table. We will be back here in just a little bit at 12:50. I'm sorry, at 2 o'clock. And we will have the rest of the afternoon presentations here at 2 o'clock. Thank you very much.
Buble.
It's everyone's favorite game show. Nobody but me.
Baby, I get a little bit jealous, but how the hell can I help it?
I hope everyone had an enjoyable lunch. If any of you are runners, of which I'm not a runner, and I don't play a runner on TV, but if any of you are runners, we're in the last lap, right? This is the final set. And so we're excited about what we have this afternoon. So we have, we'll start off first with Carl Englund, Associate Professor, Research Professor, Washington State University. So Carl will be up first, and then he'll have his full presentation, and then Reinhard will be second afterwards.
All right. Can you guys hear me all right? No? Now you can? Okay, I guess it takes a minute. Well, thanks for those who stuck around for the after lunch break talk. So thanks for everybody for showing up. My name is Carl Englund. I'm at the Composite Materials and Engineering Center at Washington State University, which is in the US. Not on the Seattle side of Washington, but on the close to Idaho side. So kind of wanted to give you guys a little bit of background of what we do at Washington State and where kind of some of the motives behind what we're going to look at here. Our lab is about a 2.5 meter squared pilot facility. We have a lot of different equipment, full scale processing equipment, hammer mills, shredders, pellet mills, extruders, hot presses, you name it. We also have a full scale structural testing lab, so we can do full scale members, walls, floor diaphragms, individual members, but we also have a lot of the analytical capabilities that most universities will have, the alphabet soup of thermal, physical, and chemical analysis. So one of the things that we do quite a bit of work with is dealing with low valued or recycled feedstocks. And often we get our feedstocks in a variety of different forms. Coconut shells up there, those came from the Philippines, agricultural wheat straws, corn stover, you name it, it comes to us in a lot of different forms. And so everybody wants to do something with this. You know, we're in turbine blade, you get an aircraft part, you get a carpet fluff, you get whatever kind of thing. The first thing we need to do is figure out how do you get that into some type of usable form. No matter what operation you're going to put on there, you got to get it into a usable form so it can be fed. So we do quite a bit of work in that. We'll break it down. We've done wood plastic composites with different types of wood and different types of fillers. We've done recycled PEEK, recycled carbon fiber, recycled glass fiber into a variety of different types of products, whether it be panels, three-dimensional panels, three-dimensional plastic injection molded parts, fuel pellets. The plastic industry likes everything in nice pellet form. And so if you want to get your product out there in the plastic industry, you got to put it into a pellet. We do a lot with chars, do a lot of biochars and pyrolysis-based work too. We also do a lot of chemical recycling. And so Dr. Zhang, my colleague, does quite a bit with mainly carbon fiber recycling and looking at ways of cheaper ways and more efficient ways of pyrolysis to break down chemical resin structures and be left with a good coherent mat. And so I didn't want you to think everything that we do there is all mechanical recycling. We do quite a bit, and we also do quite a bit in the pyrolysis side too. But I'm going to focus pretty much on the mechanical side. And so when you look at a lot of the folks that have been in our lab, like Herr Kessing, that'll be talking up next, many of them, we've probably dealt with like over 150, 200 different industrial clients that have been through there. And a lot of them want to figure out, how do I recycle? And there's probably four basics of recycling value chain that you need to address. And I know a lot of you guys know this stuff, but I want to reiterate this big time. You need to have a process or method to do it. And we all know that, whether it's pyrolysis, cellulose, mechanical, or whatever, you need to have some type of process that takes your product and put it into a usable value-added form, right? Whatever it is, you need to have that. That's easy. Feedstock logistics. How do you get that material from point A to your manufacturing site? That is something that is often overlooked. How much feedstock do you actually have? We talk about all these numbers that are associated with wind turbine blades, glass fiber composites that are out there. You get all these different products out there, and all these different numbers of tonnages that you see out there. How do you get those to your plant? What are the transportation logistics? How do you set up your plant? Where do you put your plant based upon where everything is? That is huge. That is one of the biggest things that I always ask clients when they come into the lab. And they always look like I just beat their puppy. And it's one of those things you just got to have it. You got to figure out, and then you got to be able to scale your process to match that volume. If you don't do enough or don't take in enough, or it becomes difficult to scale to that level, you're going to be not doing much for society, are you? If you decide that you want to go into a process that you don't have enough volume, you're not going to be able to answer the market. So you got to match the volume and your feedstock logistics to your product performance. Third one is product performance. So gone are the days that we can rely on recycling as a marketing tool. You have to be able to meet the product performance and the product level of your competitive products that are out there. You can't rely on recycling. That's all there is to it. And then the fourth one that I mentioned there before, scale, you need to address this for a societal need. You got to have, if you're doing a process that, only takes in a hundredth of a scale of the material that are out there, it's not really doing much. You might make a little money for your investors and your shareholders and all that kind of stuff, but you're not really doing much for society. So you need to kind of address the scale. So I usually give this talk, or I give a lecture to a lot of students at WSU. And one of the things they always ask me is, say, Carl, why do you have to replace the wind turbine? Don't they just last forever? I'm like, no, they don't. So after the first time I did this talk, I said, well, let's go over this. So why are wind turbine blades removed? Most of it is because of roughened surface. We like to think that, well, they're getting rid of it for safety facts and all that kind of stuff. It's usually the rough surface. And where do we see that? From rain, bugs, snow, hail, sleet, all that kind of stuff hitting that leading edge. And when you're down, you're swooping against the ground, you get a lot more damage on your leading edge than you would up in the air as an airplane foil. If you have a lot of erosion, pitted marks on there, you can get up to a 5% reduction every year. So what wind farm owners and the people that are consuming or getting the electricity and selling the electricity are looking at their outputs. And they see, 10 years, 15 years, I'm starting to see quite a bit of decrease. It's time to replace those blades. It comes down to money. I mean, it's not one of those things where you're going to look at this and say, oh, it's a 30-year blade kind of thing. If it's getting a lot of erosion, a lot of pitted issues, it's coming down. And it's another thing is when they go out there and they get a crane that goes out there and takes down these turbine blades, they're going to take down all, or they're going to take down a big chunk of them. That's just the reality of it is. And so you can see some of the work that's been done in the past. The talk yesterday was really great about how you fix this leading edge and make it a little more smoother and make it a little more efficient. That's great. It's a little bit hard to do that when it's hanging up in the air. And once you put it down on the ground, it's even a little bit more difficult to put it back up there. So, like I said, they're removed because of cost. So we get the blade down. We're going to say we have this blade that we need to recycle, right? So you got to make this blade, unless you got a reactor that's 150 feet long or even 30 feet long, you still have to kind of look at how you're going to break that down. And so when you look at mechanical recycling and mechanical breakdown, that's a common process that needs to go into pyrolysis. It needs to go into pyrolysis. It needs to go into any type of process that you have. You need to be able to take that material and get it feedstock ready. And so we start looking at quite a few of these things. You can see some of the work we do with carbon fibers. We did that with Boeing in the past. Some wind turbine blade material that we looked at there. And so what you do when you look at a mechanical recycling, you're not liberating those fibers, right? We're not burning the resins off. We're not solicizing the resins off of there. We're going to keep it as a fiber bundle and not an individual fiber very often. And so you're dealing with a whole different product than you are dealing with going back into a virgin glass fiber resin or virgin glass fiber. So when we look at the breakdown process, this is where things get a little bit tricky. And every type of product that you have, whether it's unidirectional, whether it's a weave, whether it's a thermoplastic base, whether it's epoxy based, they all break down differently. And that's key. And so you have to understand what you're getting in, all the different shapes and sizes of it, where it's coming from, the amounts, what kind of contaminants you're getting in there, kind of metals. I don't know if you guys knew, but they used to use lead to balance out these blades for weight. Hopefully they don't do it anymore, but you do see some lead in these blades, and it's not a fun thing to have because that's hazardous material at that time. At least in the States it is. I'm sure it probably is in Europe. So then the next thing you do is then you look at size reduction. How do you break it down? And there's lots of different ways to break down materials. You got to remember these glasses are silica based. They are going to do some damage to parts, metal pieces, and all that kind of stuff. So you have to take that into consideration on your breakdown. Once again, how much you're actually going to run through there is going to dictate what size machine you're going to be able to have there and what kind of contaminants you're going to see in there, all that kind of stuff. And then the next part that I think is probably one of the most key parts of this is if you want to start adding value and not just breaking down this stuff and just selling it to concrete guys or whoever kind of thing, you need to fractionate it out. You need to have size fractions that are consistent because you're going to be competing with commodity-based products. They're usually fillers or fibers that have a size distribution, so they have to be sized right. They have to be compositionally consistent. You name it, all those kind of things. And so as soon as you can start fractionating this out, then you can start saying, I'm going to put this stuff into this market, this stuff into this market. And then you can start looking at a diverse product portfolio that you'll have. And that's where you want to be. So if you look at this is a particle size distribution right here. Yeah, it's working. And the bigger chunks are on this side, smaller chunks on this side kind of thing. And so one of the things that we've done in the past is said, well, the cookie crumbles a certain way, right? It's going to, when you break it down, you're going to get a certain fraction of bigs and a certain fraction of smalls, and it's fractions of the stuff that you want. And so if you want to make more of these composite panels or some type of product using bigger fiber bundles, you can dictate how your curve will be set up, your particle size distribution curve. You want to put more of the smaller fines and that kind of stuff into a thermoplastic pellet or a compounded pellet like that, you can go with you can go with smaller fractions. You can also do concrete. We've done concrete since, I think we did some papers back in 2011, 2012, something like that on concrete reinforcement, utilizing a lot of these mechanically refined carbon fiber and glass fiber composites. And so if you envision this, you could also then sell a lot of that fraction to pyrolysis, to sovolysis, where they want a clean source of fiber and material anyways. You could sell it to those guys. And then they don't have to deal with the contaminants. They don't have to deal with the issues of all those other things. But you got to get that material feedstock ready. And you got to break it down correctly, or else it's not going to work. So if you look at the compounded pellets, if you look at some of the recycled fractions that you put in there, usually you're using some type of commodity resin, or you can use a specialty resin, engineered resin, however you want to look at it. Extruded, pelletized, however you want to do it kind of thing. But you got to get into a compound pellet. And these pellets, like I said, this is the international staple of the polymer industry. So anybody that wants to do plastic processing, got to probably put it in a pellet somewhere along the way. And so this pellet can then be used as a drop-in replacement to do pallets. Some pallets we did. I think that pallet right there is about a 50% load of wind turbine blade and recycled LDPE. But you can also go into under the hood parts, which is great for cars, if you can get into that market. So it's got a lot of potential, a lot of applications there. The thing is with this, is you're really competing with the fillers market in this case. So calcium carbonate talc, your cell phone, this hoover doober thing has got fillers in it. Everything's got fillers in it. And most of the fillers that we get out there, calcium carbonate, talc, mica, all those are virgin materials. They're all mined. They all put a pretty heavy footprint. They're all pretty cheap, matter of fact, but none of them are recycled. And so it's a really good market to go after. It doesn't seem like much. It's not sexy, but it is a potential option. You know, you got the sustainability aspect of it. Structural performance can be there kind of thing. It's not quite as fine as a lot of the inorganic fillers. You know, you're talking, you know, if we break down the wind turbine, we're in that 40 to 60 mesh range. If you look at calcium carbonate, talc, and those kind of, they're usually at 400 mesh. So it's a little bit bigger, but that allows it to process a little bit easier and run a little bit better in your process kind of thing. And fillers, like I said, they're everywhere. And the market growth is amazing for these things. And they're in everything that goes from food related to packaging, electrical, as you can see up there kind of thing. This is definitely an area that is hungry for a recycled product that they can put in there. But you gotta get them consistent, because the guys that buy talc and they put it into their system, that talc is really, really consistent. It's the same thing over and over and over and over again. If you're going to start dealing with recycled material, the first thing they're going to think is you got a lot of variability in it. And you got to put that in, you know, you got to put that to bed right away. And so if you look at this, you know, we did some work with fillers, usually pretty fine material in this case. Had some, the RCFC right there is carbon fiber. I think this is 70 mesh or lower. Can't remember exactly. This is about a 30 or 40 mesh. Recycled wind turbine blade, talc, calcium carbonate, and the control is just the straight up, I think this, yeah, PP and PE, high density polyethylene. You can see you definitely get an improvement. It's not great, but it's definitely there. And it processes really well. And so a lot of people like it, and it's got the recycled aspect to it. So if you can get everything the same, it's a good place to be. We did the same thing with a lot of these carbon fibers with a stiffness evaluation on fiber loading kind of thing, MOE and MOR. You can see with the carbon fiber, of course, is going to be a little bit higher, a little bit stronger and stiffer. The glass fiber is a little bit lower, but they still cause quite a bit of increase in strength and stiffness. So we're pretty happy with a lot of those things. The other thing that you can sell these fibers into is the wood plastic guys that tracks the fiber on the, yeah, composite. Who was it? Nova? Who is the guys over here in Europe? Novatech. Yeah, the Novatech, all those guys. So I actually presented this back in 2016 to the Composite Lumber Manufacturing Group kind of thing. And if you look at it, you know, our MOE, our strength stiffness of the product was really quite comparable to wood. Actually a little bit better in a lot of cases. But the key on there is you don't have the moisture issues of that you have with wood. And so we're like, well, Carl, you're dealing with wood, you know, it's cheap, yada, yada. Well, that's the nature of the beast right here, guys. I hate to put it to you this way, but that's the way it is. That's the nature of the beast. That's the place where we're going to have to compete, in my mind. The other thing that we've done in the past, and Dr. Herr Kessing will talk about this a little bit more, is our panel process, is where we just basically turn them into, as you can see in the back there, composite panels or specialty panels. If you look at pretty much everything around here, it's all panel assemblies, and they're everywhere. And there's a lot of market need for specialty panels. Basically, in this case, you can use a lot more of the composite or the wind turbine blade. This is about a 96% wind turbine blade and 6% or 94% and 6% resin, I think, in this case right here. And it makes a really nice hard surface, and it's a great little product. And Reiner will talk a little bit more about that, but I'll kind of give you some of the structural aspects of it. If you look at OSB, which is a common, we build a lot of stuff in the States with wood, not as much over here, but OSB is, you know, is quite common, and it has the same strength properties and similar properties as an OSB composite panel. But the big thing about it is that since it doesn't have any wood in it, well, hopefully I'm not shining people's eyes there. it doesn't have much water absorption. So you get a panel that's really hard surfaced, which can take overlays really well. And you see that over there, and it doesn't absorb water. It's got a lot of good places that it can go. A lot of places where wood falls short. This is where you put this stuff. We've also done, like I said, we've done quite a bit in pavements in the past. I won't get into this too much, but we did some work with pervious pavements with Boeing, looking at putting those in there. And one thing that you'll see in there is, you know, if you put fibers into concrete, you got to take something out or it diminishes something, whether it be the binder that diminishes down. A lot of times it's the aggregate that you put in there. And so when you take aggregate out, you kind of lose the compressive strength of it, no matter what you do. No, it doesn't matter how strong that fiber is. The rock is a lot higher in strength when you're stepping on it in compressive load. And so it doesn't give you as much compressive load. If you keep the compressive load the same as a controlled specimen, you're doing well. Where it does really help out is right in here where you're looking at the ductile failure. You actually start to, you know, if you look at just concrete, just aggregate in there, bam, it snaps right away. But when you put fibers in there and you control the fiber, like this is done with very controlled, it's not just throwing everything in there. You got to control what you're putting in there. And then you can actually realize that fiber strength and stiffness a little bit better. And as we all know, it's not just wind turbine blade. This, I wish I could find a more updated pie chart. This is 2016 and it's relatively similar, but you can see that little small pie right there, that's the wind energy. So glass fiber composites are everywhere. They're 18 to 20 times more prevalent than carbon fiber. 18 to 20 times, that's a lot. So airplanes, all the hoods and the shells of RVs and buses and trucks and trailers and canopies on it, that's all fiberglass. You start getting into those markets, my God, it dwarfs, it dwarfs what you're gonna get on wind turbine blades. And so those are the things you gotta have. You gotta have a recycling method that's robust enough to handle that. Because as soon as you start opening up your doors and saying, I'm gonna take wind turbine blades, I guarantee you there'll be 20 people for every one that's telling you, hey, I got this other fiberglass product that, can you use this? Can you use that? What are you doing with it right now? Throwing it in a landfill. So, things to think about. If you got any questions? I'm here right now. I'll try to go a little bit earlier so I can get Reinhard on, but I'll leave it as that. Yeah.
Couple questions real quick before you get up.
Yeah, super fast question. We have a lot of discussions sometimes with our investor about the volume, right? And whether it's coming, not coming, and so on, right? So many, yeah. And then we show also the pictures about, you know, all the rest of the industry, and there's plenty coming back. I mean, like more than we can handle, right? So wind turbine is just a part of it, also here in Europe. So, but did you kind of look more also into processing, for example, like we looked into processing maybe both hulls, but we said like, okay, we only want them like sandblasted, taking off, you know, all this anti-fouling stuff and so on, right? So have you kind of a little bit like looked already into other products? So because that would be actually a really like enhance a lot of business cases actually for a lot of people here. Because it would give a bit more feedstock security, you know, for an investment. So I would be curious if you have already looked.
Yeah, no,
further
you're
looking at
100% right.
Yeah.
Yes, we have done stuff with boats and with RV parts, and we can work with them. But yeah, you're right. You kind of want it. You don't want to have all the glass and everything that comes in a boat. What you really want to have start coming on here is a supply chain developed. You don't want to have one company or your company or whoever doing everything. And so there's guys, the same thing with recycling airplanes. You know, there's a lot of good computer, a lot of good high-end metals and that kind of stuff that you can get out of an airplane, but there's also a lot of fiberglass and carbon fiber that's in airplanes that don't have a home. Well, if you could start building that supply chain up and say, hey, I'll take that clean fiberglass from you. And if it's cleaner, I'll give you money. If it's dirty, then I'll charge you for it, kind of thing. You start building up those kind of supply chain development concerns or potentials, That's where it kind of comes into. The same thing with boats. There's lots of really cool things that people want on boats, the metal railings and all that kind of stuff, the navigation, the glass, those things can be recycled. And as soon as you can find a place for the fiberglass to go, then that makes a better business model for them and everybody works together, I hope.
Yeah, that makes sense. I mean, like, yeah, do you have to build the full supply chain? I think, you know,
Yes.
if
That- and I
everybody
think that's-
claims I have the perfect method, no, this is not gonna work. You know, like,
Yeah, and
it's a
and-
corporation.
and the whole thing, you know, I didn't talk too much about the feedstock supply is just getting master services agreements with the owners, the Vestas, or the landowners or whoever to just get that material. That's a 3-year process. And it's not easy. But once you get in there, or if you don't get in there, then you got to redo, you know, this certification every time. Once you get in there, then you're good. And so, but it takes a while to get that. You get your ISO certification, you got to get all these things done, EPA regulations, all that kind of stuff.
So Carl, what you're saying is don't put all your wind blades in one basket.
Yeah, basically.
Very good. Okay, one last question or? Very good, Carl. Thank you so much. So Reinhard is a very busy individual. He's a co-founder, partner, and CTO of Continuum Group and founder and CEO of Custom Engineering.
Yes, good afternoon, everybody. Thanks for sticking around. Yeah, I usually, in order to explain the whole business and the whole technology, I need 2.5 hours. Now, you have to reset the clock here. It's 17 minutes, it's not going to cut it, but I'll try to make it as painless and at the same time provocative as possible, because, you know, we're claiming some things, but the good news is we have proof. And today I'm blessed really because I have 2 live persons here that can attest to many of the claims that I'm saying or giving here. Okay. So yeah, let's go back to the past a little bit. Allow me 1 minute to talk about our relationship, you know, with Professor Dr. Carl, who you just heard. I remember very well, and I'm sure he does too, you know, in 2000, let's call it 2003 or 4, when we met first in his laboratory, you know, I dragged in things and he said, Reinhard, what are you doing? Are you crazy? What are you trying to do? I said, I'm trying to recycle the non-recyclables. At the time, it started with carpet. It went to automotive waste, car interiors, headliners, dashboards, side panels, seats, everything. That's how it started. You know, I come originally, just like Carl, we have a strong woodworking background, but that gets boring very quickly. So we started, and my business was doing good, so I had time and money. So I said, I'm going to try something that nobody else has done. So since 2004, I have been starting this technology, which, like I said, led to where we are today, which is really interesting. One thing, it's not in the presentation, but I want to mention it because the forum is regarding wind turbine blade recycling. Of course, this technology which I'm introducing is also suitable for marine aircraft and all the other ones. Absolutely. Okay. So let's be clear of that. One other thing I forgot, so I have my little cheat sheet. I heard a lot of people talking about, well, we can't use this and we can't use this ingredient. And here's the good news. And the other discussions I heard was, well, there's already 25 years of wind blades out there. Then I heard there's wind blades that are still being installed today that are not officially supposed to be recyclable. The news I got for you all, especially the Vestas, the Siemens, all those guys, every blade you have ever made in the past is already 100% recyclable with our technology. I think that's a fair statement. Okay. Now, where's the thingamabob? Which one is it? Top? Arrow, right? Okay. That's the, you know, the official title. That's me. Okay. Now, we are fully aware, and I'm skip some of these. I'm going to skip because of time. We are fully aware of all the other methods: pyrolysis, solvolysis, hydrolysis, mechanical. The bottom one is the one I'd like you to read. All these technologies have their limitations. Some cannot recycle 100% of the blades. Most of them cannot create toxic or unwanted byproducts, are not ready for industrial scale, and either they are not environmentally friendly or they're not profitable. Okay, now that's a strong statement, but we have engaged independent parties to verify that and to check into our technology and even in the business case. Among them, Washington State University, and this goes back many, many years, I almost said decades. Living proof is there, Dr. Karl. ORE Catapult, I'm sure a lot of you people know them. They have provided us this year in May an 83-page document in which they confirmed our technology. In fact, they didn't believe me in the beginning. So I said, well, come with us and we will show you that we make from this wind turbine material, we make these panels that we are promoting. And I dragged them to our machinery and equipment supplier, Mr. Buchwald. Paul Buchwald happens to be here. He's our machinery and equipment supplier from Diefenbacher in Germany. So they verified everything, gave us the green light. Same with Ramble. It's based in Esbjerg. They did the same thing. So they checked our products, they checked the technology. Now, and other accredited people said, okay, you're right, this does actually work. Unanimously, they said, what you're doing does work. What you promise does work. And here's, another thing I'd like to mention, the end product that we make is recyclable over and over and over again. I think there's not too many other technologies that can state this, okay? There's just an example, the 12mm panel blown up, 3-layer panel. There's samples there, you can feel them, touch them. I buy you a case of beer. If you can break one with your bare hands, it's not gonna happen, so. All right, now, the comparison with all the other technologies. Just read the headline. We could debate on this table for hours. I don't want to. Basically what it says, every technology has their ups and downs. Okay, so where it starts, here are 5 points on my list, and I'm challenging every other technology and say, okay, if you can meet all these 5 points simultaneously, then let's talk. Profitable. Is your process profitable? I have some doubts in some cases. Is it environmentally friendly with the lowest CO2 possible footprint? No toxic waste or byproducts. A lot of them fall off the cliff there. The entire blade and contents are recycled. I heard nobody saying, yes, we can use everything. Everybody wants to get rid of this. We have to sort out this. We don't. Large industrial scale ready. I haven't heard that. Some exceptions. The end product recyclable over and over again. So, what amazing high-end products can be made from this technology? There's just some examples there. And again, if I had more time, I'd be happy to talk to you about details, but I'll just switch through. The technical specification and data sheet is, it's just amazing. For instance, if you put these panels, submerge them underwater for 24 hours, you take them out the next day, and you measure the thickness swell. The thickness swell is going to be less than 1%, not 1 millimeter, 1%. So if you have a 10mm panel, 1%, you need a micrometer to measure it. So it is a watertight product. For instance, unfortunately, more and more floodings happen. Basement is, finished. So with these panels, you put them on the wall or floor, whatever you want to use them. After the water is pumped out, you take your high pressure washer, you clean it, let it dry for 3 days, and you can, pretend nothing happens. So that's another product. But please do take photos, or you're going to get a copy of this. the mechanical properties are amazing. All right, just a technology overview, and please forgive me for blanking out some of the vital parts, but I just wanted to present, this is not a dream. Remember when it started, and it has been perfected since, and it has been verified, and we have, for each and every machine that we're using in this process, we have run live tests with our machinery and equipment supplier. Just a few, a rough overview of the process steps. I'm listing here 23, if you want to call it. I'm not going to read them all to you, but you can see, what goes in, where it is in the middle, and what comes out. And it's a pretty amazing product. We do it from 6 millimeter thickness as the thinnest panel up to 35 millimeter. We could do even 40 if we had to. All right? Now, market size, end of life wind tunnel. I'm going to skip that. We had 15 slides so far, most conservative and so forth. Where are the blades? Again, I'm going to skip it. We don't have time. My view or vision is that we should recycle profitably, because unfortunately, when I talk to investors, I talk to banks, they say, well, Reinhard, you have a wonderful thing, but can you make money with it? And then you better have a robust business plan, which shows that you can do this. You can get the material, like Dr. Carlson, you can get the material, you have enough feedstock, and you have an end market. And when all those boxes are ticked off, then you have a real viable business case. And we have matched those two. So this is very important. Technology summary. The proven and tested Kescon technology utilizes 100% of the blades. Just let that sink in, 100%. Nothing goes out. The metals we sort out, ferrous and non-ferrous, but they do go back into recycling, no question. We voluntarily sort out carbon fibers if there are, not in the old blades, not so many, embedded carbon fibers. We sort them out because they're too valuable actually for our process. There are no byproducts, no waste in our process. We have no flames, no stack, no smoke coming out anywhere, no effluent water. It's powered, the entire plant is powered by 100% green electricity. The metals, ferrous and non-ferrous, as well as CF, I said it already, are coming out. The whole process is totally encapsulated, which means there are no fugitive dusts. As soon as the blade enters the first machine, it is, you cannot basically see it anymore. Everything is totally encapsulated. There are, suction systems, filtration systems, class H. I don't know if anybody knows what class H means. It is such a fine filtration system that you could theoretically handle asbestos. In technical terms, it's 0.1 milligram per norm cubic meter that may slip through the screen, through this filter, yeah. So it is extremely environmentally friendly. So this is super important. You can't just make something and, when I see some of the photos where they create dust, and this is impossible. Plant designs, capacity. Also, the other one was all these, the materials, the dust that is being extracted and filtered ends up to be collected and put back in our product. We are not sending anything to the waste or landfill or whatever. Everything goes back into the product. Even when I have the boards and I cut and trim them, that material goes back in the process. So there is no waste leaving the factory, absolutely nothing. Plant designs from 5 to 100 tons per day, ready and fully developed. I have in my computer even, I can show you the drawings, layouts, flow sheets, everything. And it's feasible. Energy efficient, clean, safe, and state-of-the-art machinery and equipment supplied by industry leader Diefenbacher. Hello? Here he is. So if you have questions, if you don't believe me, you can ask Mr. Buchwald. Now, last comment, commercial summary. ROI on a plant with a capacity of 100 tons a day is approximately 6 years. For those that are interested in numbers or financials, that's not too bad. I mean, I've seen better, yeah. Bitcoin is, but I've seen them also lose. So 6 years, it's a good start. Investment opportunities for factory financing are offered. Technology licenses can be offered for a number of countries. And the current full-size plants in final development stage are 100 ton per day in plant in Esbjerg, Denmark, by Continuum, or a 10-ton plant in Portugal, JFR Enterprises. That's what, is in the making right now. I do agree that these plants cannot be or shouldn't be, much larger than 100 tons per day. Why? Because of the logistics. You don't want to transport a blade or blade sections even for more than 200, 250 kilometers. So it's much better to strategically position smaller plants all over Europe, excuse me. So, any questions?
Any comments or thoughts for Reinhard?
I'm stunned. No questions. Okay. One thing I'm not sure if I mentioned, to us also, it does not matter if the filler in the blade was PUR foam or balsa. It makes absolutely no difference to us. Okay. All right.
Yes. So, I'm a bit, okay, you told us that we can all go home now. So because you have the solution, fine. Because we all kind of believe in our stuff as well. But I think the main part is, or the big question that we all have is, it's fair enough that you say, I can recycle it within my facility again and again. But if you want to put it like into like a building, as a building material, you have to put flame retardants into it, most likely. So that's hazardous material. And it will go out to like a lot of craftspeople. They have to cut it on site. They're exposed there to the dust. So it's not what's happening in your facility. It's about like what's happened outside in the use of the material. So the question is there any application for that or any feedback from any craftsmen? Because they have to saw it. There's a lot of dust. It's usually pretty itchy, with glass fibers. And then the question is how to actually get it back. It's fair enough it's a matter of collection. So when we take the example of like Megawood, right? Or, that was presented here by a couple of people as a partner. They have a really interesting thought. First of all, they only take a few parts of the blade, but instead of selling the terrace to people, they would just want to rent it out. So to make sure that they actually get all the material back that they have put out there, because they can also recycle that in their wood plastic composite, right? So that's an interesting idea. So the question is not whether, we are like super duper on HSE, in our plant, but the question is what happens with the product afterwards? Do we even have a chance to collect it if we put it out there? And does it, is it safe actually to use? Like for like everybody's like craftsperson if it's in a building industry. So I think this is kind of the elephant in the room question.
Yeah. I mean, you had several questions in your question speech. Yeah. Let me start with the fire retardant. You mentioned that, that when people put on fire retardant, actually, we do offer 2 types of fire retardant because inherently that material is not fire retardant. It's class C if you don't put anything on. We do reach class B, which is the highest, unless you have stone or glass. There are 2 methods of getting the fire rating up to a B1. One is, and it's no secret, we work with a company from Belgium. It's called EcoChem or Incendin. They have recently been part of the Incendin group. They have a fire facer, which is actually a thin layer of impregnated fiberglass mat, which we laminate. And I can show you some of these samples, even the little one that's on my desk there, that has that fire facer on there. And then you put a decorative foil on top of it and that you reach it. The other one is a liquid form. It's like a milky solution. There's also the bigger panel, the thicker one that has this one. Neither one of them are toxic. So, you know, I don't agree when you say, well, if somebody puts a fire facer, we do have a rule, of course. If somebody uses lead paint, you remember our grandfathers, they use lead paint for their cars and whatnot, so it doesn't rust. No, we cannot, you know, if it's a super contaminated panel, we cannot take it back, of course, you know. But we do offer, that's a policy, that end of use, you can bring it back to the factory and we take it back. So that's all we can do. And then it's up to us, of course, to say, well, look, this looks all right. You know, a laminate, we don't care about. That's fine. That goes through the process. You'll never find it again. Lead paint, I would shy away from it. So yeah, there's going to be an inspection process, but we do offer to take our end of life product back. Yes.
Final question. Because we know what stuff is in the blade, so you're just basically then just reshaping it in your product, right? So all the, you know, sulfur, chlorine, bismuth, say, whatever. Do you have like, what type of quality system do you have up front to ensure that you don't have like, you know, really some very hazardous stuff that we actually found in the blades?
Yeah, okay, I understand what you mean. Maybe I should, if I have the time, I should go a little bit into how do we manage our material influx. We have, for the 100-ton a day plant, we have a 6 hectare, 60,000 square meter storage yard in which we store the blades basically based on 5 to 6 groups. The ones that have a balsa core go on this pile, the ones that have, you know, very high, how should I say, fiber content go on that pile. The ones that contain PVC go on that pile, and so forth. So we have 5, 6 groups. Then what we do is from there we draw for the next day onto a daily laydown yard list. So we create a mixture, and that needs to be constant. 3 of those, 2 of those, half of this one, and 2 of the other one. So at least what we're doing is we're not sequentially saying, okay, we're going to use this batch now, and we're going to use that batch. So it's always a constant mix. And of course, you know, we demand MSDS or SDS or material passports. We fully realized that some of the very old blades where the OEMs went out of business, we don't get anything. So we have to do our own testing, and that goes into our own database. But the materials that are in there, you know, the heavy metals and so forth, I agree. And guess what? Even when you put that into the cement kiln, and if I had time, we could go into part 2, you know, cement kiln, everybody says, yeah, this is a good thing, energy recovery. I got news for you, it's not. So, no, good. Because of all the heavy metals, because of the HAPS, hazardous air pollutants, and I mean, I have proof. We've done a lot of research there. Just, you know, one simple idea is you go to your municipal waste to energy plant and say, okay, here's 10 blades, please put them in your oven. They say, go away. Toxic waste, we don't do it. The cement kiln industry found a loophole because they're not controlled for emissions, and that's going to stop too. So, but what's in the panel, you know, we are also clear that none of our panels will be used in an application where there will be absolutely no top surface finish. So either we will have them laminated or painted, or you see the many different possibilities. So whatever is in there in micrograms, nanograms of, it's going to be covered. And by the way, wood-based products, they have the same problem. I have been doing a project in France. This is probably 30 years ago. There was so much lead in the trees from the World War II that you have no idea. I mean, the panels that we made were actually toxic waste. So just to give you an idea, that's exaggerating, but it's true. Yeah.
Thank you for everything. Sorry, we're running late on time for the next 2 presentations. Reinhard, I really appreciate it.
All right.
Thank you very much for stimulating.
Thank you.
So we have two more today. Daniel Grisanti, Refresh Project Coordinator for ARENA, and then Jaime Moreno, Project Manager, Energy, Climate, and Urban Transition Unit for Tecnalia.
Okay. So, my name is Daniel Grisanti. I'm the project coordinator of the Refresh project. I'm here with my colleague Jaime from Tecnalia, which is in charge of the part of the decision-making tool you will see after in the presentation. I don't know if you want to introduce yourself or let's go. Okay. I start with a general overview on our consortium, which is composed from 11 partners, in which we have waste recycling companies, engineering companies, and research and development entities, while we as ARENA are the project coordinators, and the UCA company leads the communication and dissemination stuff. This is the concept scheme of our project that aims to recycle the wind blades from the decommissioning till the end product finished to be put on the market. So we take into account the decommissioning when a blade is dismissed, and then we aim to develop the traceability and decision-making tool, which aims to do some market check, the technical check of the blade to decide which is the best recycling process to send it currently. We develop in the project different recycling processes, the mechanical one, the thermochemical, and the other means to recover the blades as the repurposing or the reuse. And so this is the whole concept of our project, which, as I said before, takes into account from the decommission of the wind blades till the end product. So this is our value chain. So here's the partners that take into account the various steps of the recycling process of the wind blade. So we start from the decommissioning. As I said before, there ETAF and MTBS partners that take into account the pre-treating of the wind blades, and then our partners for the recycling phase, GIS Recycling, Gencraft, and Circe, and Ecolab, which aims to produce other products like composite panels, recover fibers from the thermal process, and chemicals as well with the pyrolysis process, and also the recover energy. And then other players like SETMA, which is a research center, Tecnalia, and Acciona that works on the eco-design and to think about how wind blades can be repurposed after the recycling processes. Okay. Just to give you the timeline of the project, the project started the 1st of January 2023. So we are currently in month 22 of the project. It was intended to be split in two parts, the design part from month 1 to month 18. Then there was the milestone from the European Commission of the Go-No-Go, in which we received the go last month. So the process, the project will be proceeding successfully to the second part, in which the real integration testing and the process will be deployed, as well as the proceeding from the preliminary LCA analysis, which was done only in theory with the theoretical data, in which now we will be doing this with the real data of the process we are developing. So this is some pictures and some of the activities that are performed from our partners. So from the pre-cutting phase, from Etat9, then the shredding and sorting activities from NTB that aims to develop a portable shredder for our process, in which we can obtain different granulometries for the pre-treated glass fibers. The mechanical recycling from GIST Recycling, in which they have already a line which is working. The aim of their process, the aim of their progress in our project is to upscale the production. So to build a second line to upscale the tons per year of material that can be processed, and the main output are panels with different densities and other products. This is the part of the pyrolysis and solvolysis by Circe that will be presented by my colleague Ignacio. So I will be leaving this part for him later, just after my presentation. Otherwise, that's spoiler. So, but the idea is that one of our technologies is the degradation with pyrolysis assisted by microwaves and on a non-electrical one, which brings some benefits in terms of diffusion of the heat and the preserving of the fibers that don't get damaged from the temperature. As you can see, the recovered clean glass fiber have not so many textural damage due to the relatively low temperature of the process, as well as the recovering of pyrolysis and syn oils from the pyrolysis treatment. This is the GenCraft technology, which has been presented yesterday from Marcin. So I will be brief about this. This is another thermal recycling technology we are using in our project. So it works like the continuous and batch line that has been tested, and in which the next steps have to be basically the commissioning and the real installation of the new line that has been tested and processed in the first phase of the project. This is the eco-design strategy we foresee for our project, which main is focused on the repurposing and the recycling of the blades. This is where our project stays for the end of life wind blades operations. And these are some of the application I was also talking about before, like the panels production or maybe other application like concrete structures, which is actually part of the project taken care by Tecnalia. So this is the environmental life cycle assessment that I was speaking before, which is like we have performed the theoretical part with the theoretical data, and now the aim is to upscale this with the real process data that we'll be developing in the next month, alongside with the deployment of the various processes. So these are some results of the environmental benefits that are foreseen for the analyzed processes in our project, showing the savings in terms of equivalent CO2. Okay, and then you can continue with the.
Okay. Thank you, Daniel. So my name is Jaime Moreno. I am a project manager at Tecnalia. Tecnalia is a research and technological center located in Spain. And I work in the construction sector, developing different solutions for improving the circular economy, the digitalization, and the industrialization of the construction sector. And we try to have a different synergy with other sector and other economical sector also, for having a cross action between the sector. And this is the case of the REFRESH project. So here we try to employ the fiber recovered from the thermochemical technologies for developing new 3D printed mortars for the wind towers. And well, with the glass fiber, clean glass fiber, we try to develop this mortar for improving their flexural strength and also the drying shrinkage of the mortar. And the other activity that we are performing is to develop the digital tools of the project. In this case, we will develop a blockchain-based traceability tool covering all the value chain of the decommissioning or recycling processes of the wind blades. And well, the purpose is to obtain a real-time tracking of the different information we can obtain in the different from the different stakeholders involved, to have a transparent information and a good sharing of this information, and to have a secure data storage of this information. For what? For improving the quality control, for improving the efficiency of the different processes we are applying in different step of the value chain, to increase the confidence and the secondary materials acceptance. This is critical in the different sector when we valorize the waste and we use those valorized waste as new raw material, secondary raw material in new product. And we also try to provide confidence for the for improving the regulatory compliance. Sorry. Okay, and with those data collected, we can employ them. We will employ them for developing a decision-making tool. This decision-making tool will be employed for the optimization of the different steps. Okay. So here, well, we will employ an existing blockchain platform for traceability. We have two different platforms, TraceBlock and TraceToken. The second one is an updated version of the TraceBlock. But well, here you can see in this video that we can track all the information of a given value chain. In this case, we have to adapt the value chain to the wind sector, wind turbine sector, and we have to adapt the ontology on all the information we have to incorporate in the platform. Okay, here you can see we can track with maps and all the provided information, all the materials. And well, and with the information, we will feed a decision-making tool. We will extract the information from the traceability platform, and we will feed a decision-making tool that will be based on technical criteria. We will provide technical criteria, environmental, economic, regulatory, and social criteria in order to optimize the technology we have to employ, the environmental impact, the economic impacts, and well, finally, how to improve all the value chain of those materials. And we also we will also work on the digital product passport. It's a hot topic now in the European Commission. The digital product passport. We don't know exactly what will be the information we have to provide to the digital passport and the ontology of the information. But it will be a basis, a digital basis for improving the information we can provide to the digital product passport for this, from the decommissioning to the incorporation to a new construction product or other type of product. Okay. And well, what are the challenges here? Most of them are technical challenges like the system integration, and other are mainly focused on data accuracy and the way to obtain the data. No, here we normally have a big problem is to obtain the information and the data from the different stakeholders. So, well, in this case, another in the construction sector, another sector is almost impossible to have the stakeholder participation between them and to have the information of the materials of all the process or so on. So it's important to have a real participation and a real incorporation of those data in the platform. And what is the future? So the cross-industry material change, of course, the synergy between industries. And for me, one of the main work that we have to provide in the future is the standardization, the digital product passport information to be provided correctly. And also we have to involve maybe the insurance company, because we are talking about some structural application. And well, here we have the problem of standardization. The regulation should provide well, this framework, this standardization framework for the use of a structural product. And we have also to involve the insurance company in order to guarantee that those material can be used, no, in a safe way. And we can also work on extended producer responsibility. Okay. And that's all from our side. Thank you.
Thank you, gentlemen. Do we have any questions?
Thank you very much. That's very interesting. I just picked up on the part about extended producer responsibility and also about the LCA. Do you think those tools could be used by the developers in terms of selections of blades that, you know, in time become more recyclable and drives the right procurement process? Sorry, I do speak quickly. I don't know if...
No, yes, but I don't know.
Yeah, sorry.
What exactly to answer.
So you've got some good material content, LCA, extended producer responsibility. If that's by blade, the developers who are installing turbines, they have a choice of which blade to purchase. And would the developer buy the blade that would be shown to be more recyclable at the end of life? Maybe it's a chat afterwards.
I mean, I don't know what to answer, sorry.
That's okay, no worries.
Maybe just a quick question for me. It might be that it's getting a bit late in the day, but I would like more of a concrete example for the decision-making tool. So what kind of decisions do you envision being made through the tool?
So for example, we have been talking about a lot of mechanical technologies and thermochemical technologies. So providing the data of what type of blade you are decommissioning and the different obtaining the information of different part of the blade, you can make the decision of what to do, what to cut them, and what to recover them, or what mechanical technology or other technology apply. So we had to develop the decision-making tool. We had to work on that, but this is the idea. We can apply also artificial intelligence, but it will not. It's not the case of the project.
Great. And for the regulatory compliance aspect, it's just European regulations that go into it, or also national, regional?
Sure. We will go to national level, yes. At the end is European, more or less regulation, no, depends of the countries.
Clear, thanks.
This is the idea, no, Daniel?
There are some regional differences.
At least in Spain, we will not cannot apply all the regulation of all the countries, but
I've got one over here. Thanks, Jaime. Thanks, Daniel. I may have missed this in the presentation, might be a stupid question. Is the blockchain product deployed and ready to be used? And who's your target customer?
I don't heard.
I'll go again then. Is your product live in operation? And who's your target customer of this blockchain service?
Yes, it is commercialized, yes. But we are not software providers, so we develop, we adapt the different solution and we sell it to software companies. But the final customer can be the construction sector for the construction demolition waste. They are employing that, so we are selling it adapted to this sector. In this case, for the wind turbine blades, and also for we employ it for all the logistic of textile or food industry. Okay, so maybe they have other customer, but I don't remember now.
Okay, but your direct customer was a software company, was that right?
Yes.
Okay, thanks.
Because we are not software providers, so we sell it to other software companies, adapted to the needs of the final customer.
Thank you.
Very good, gentlemen. Thank you so much for your time and presentation. So we've spoken to Ignacio before, so he's going to come up and share a little bit, a technology project manager for Circuit Technological Center. Thank you very much for wrapping up our time. That clicks a bit.
All right. Good afternoon, everyone, and thank you for being here till the very latest talk of the forum. Thank you very much. Yeah. So, okay, let me share with you some insights on a technology that hasn't been showcased before in these 2 days, which is the thermochemical recycling of the wind turbine blades assisted by microwave heating. My name is Ignacio Julián. I'm Technology Project Manager at CIRSE Technology Center. So first of all, let me summarize briefly what CIRSE is. CIRSE is a technology center that helps the industrial partners, as many of you, to increase your competitiveness in the fields of energy and sustainability. And our main aim is to fill the gap between the research and the needs of the business sector. So our business model is as follows. We start developing from bench scale technologies at TRL 3 to 4. And we increase the maturity of the new technologies by getting competitive public funding and keep on developing the technologies. Once we have something that can be exploitable, let's say, we contact companies and we join the industrial partners to assess the viability and the profitability of this technology. So afterwards, we transfer the results to this eventual company, and we enhance the partner competitiveness, generating private income by licensing our initial technologies. After that, within the process, we anticipate the future challenges and keep the partner informed, and we reinvest the incomes in improving the current line, research line or innovation line, creating a new one. So we only get funds from public research and innovation projects and private contracts with companies. There is no baseline funding from our region or the Spanish government, so self-funded. Our numbers or revenues, let's say, or incomes are about 20 million euros last year, so 11.5 coming from competitive public projects and 8.5 million euros through private projects. We are very active in European projects. We are coordinating currently 20 different innovation projects, but we are participating in more than 71. We have more than 300 private contracts signed last year, and 85% of the bill comes from the satisfied clients, which repeat with our services. Essentially, we are 300 people compared to the company that was presented yesterday with 5 very senior guys that accumulated more than 200 years experience. We are a very young group of people, so the average age is 37.5, so I'm exactly in the middle, the average one. Circa 30 PhD people there. The gender balance is quite okay, 2 to 1. And we have people from 17 nationalities. These are the innovation lines in which we work as a technology center. So generation and renewable resources, smart grids, mobility, hydrogen and renewable gases, artificial intelligence and digitalization, and the 3 topics which somehow frame the innovation that I'm gonna show you afterwards, that are industrial technologies, efficiency and decarbonization, and recycling and circular economy. Well, why using microwaves? Which is the advantage of microwave heating? As you may know, microwaves are a certain region of a radio frequency that involves electromagnetic waves with a wavelength from 1 meter to 1 millimeter. Out of all this range, only a few frequency bandwidths are available for heating. Otherwise, they could combine and interfere with radio waves or Bluetooth or etc. So only 2.45 gigahertz and 915 megahertz can be used for microwave heating, at least at industrial level. What do microwaves do? They have the ability to polarize, to change the dipolar moment of molecules by interacting with them. So how many times per second? 2.45 million times per second, a dipole is vibrating, is changing its position. This generates a kinetic moment, and this is transformed into heat. So the heating ability of microwaves is very selective. There are molecules that can be irradiated and heated, and there are molecules that are completely transparent. And since we are talking about wind turbine blades that have different components, and some are susceptible to be heated by microwaves as some, others not, this gives us a very competitive advantage, as you will see later. For example, these are curves of heating of a material under conventional heating, let's say by electrical heating with some resistances. The curve is more or less like this. And under microwave heating, since the whole electrical power is condensated in the sample to be irradiated, the temperature increase is very drastic. In a matter of seconds, you can heat up to, let's say, 500, 600 degrees Celsius samples that are 1 kilogram in volume, more or less. If we apply it to, for example, solvolysis, you can see how a system, a tank, a stirred tank, can be heated in terms of time required to reach certain temperature. under conventional heating against microwave. Microwaves are these green ones. So that means the heating time, it's reduced by at least 1 order of magnitude. In our case, by 20 times. And a key advantage of microwaves, as commented before, is that some materials are susceptors and some others not. And gases are not susceptors at all. So if we kick off a certain, let's say, chemical reaction at the surface of a solid, and these molecules, these vapors, pyrolysis vapors, come into a comparatively much colder environment, the chemical reaction stops immediately. So we can have a control on the type of molecules, the type of compounds that we are generating, and in the end, the composition of our pyrolysis oil. This is a key advantage, I would say. So, yeah, for wind turbine blades, this is more or less the configuration that we have. So fibers embedded in a matrix, either of epoxy or polyester. And the heat transfer of these two kinds of resins is very poor. So under conventional heating, the heating source need to be at much higher temperature, or at least beyond the temperature of the sample to be heated. So it limits the recycling process controllability because it works the other way around. So when the vapors are generated at the sample surface, they become a chain reaction at higher temperature in the surrounding atmosphere that is comparatively hotter. So we invert the direction of the heat flow, let's say, from the core of the sample to the outside. So based on this, the key advantages of microwave assisted heating is the fast, selective, and volumetric heating, as already said. Enhanced energy efficiency. I haven't talked about this, but there are many papers that say that the energy consumption under microwave heating is at least 3 times lower than that under conventional heating for the pyrolysis of carbon and glass fibers. Lower pretreatment requirements. We do not need to pre-fuse or pre-condense the resins before entering the main reactor chamber. We can feed directly the shredded parts from mechanical recycling, for example. We have an enhanced control over the pyrolysis process and oil product distribution. And of course, we have drastically faster startup and shutdown procedures due to this thermal gradient. And of course, straightforward electrification. So we can run a microwave pyrolysis unit using electricity, for example, from a wind turbine blade. It is in nearby. Okay, why thermochemical recycling assisted by microwaves? As said, because we can, if we know the kinetics of the reactions that are taking place to degrade the epoxy resin, which is this molecule, we can control and enhance the production of some molecules detrimentally to others by working at lower temperatures in the surrounding atmosphere out of the sample. Working at lower temperatures is also interesting because we are able to reduce the degradation of the reclaimed fibers. As you can see, the Young modulus, the tensile strength, and the strain to fail are closely, they are similar to those of virgin fibers. As you can see, there is a decay of up to 10% by this process. We can identify the molecules that we are getting out of the process and their abundance, and we can sort them to be employed for the final uses, for example, at the petrochemical industry or the plastics industry. And moreover, and this is important, at these low temperatures at which we perform the experimental assessment, the degradation of the resins is circa 100%. it's better for epoxy, a little lower for polyester, but still more than 90% in all cases. So these are the bench scale experimental setups with which we carried out the first assessment. This is a pyrolysis unit that has a power of 3.2 kilowatts through 4 magnetrons that release microwave irradiation into the sample. The arrangement is a fixed bed full of shredded FRP parts together with susceptor particles, that is a particle that absorbs the microwave heat and releases it into our FRP. And these are the fibers out of the process. As you can see, these are glass fibers covered by coke. So if one wants to get a completely clean fiber out of pyrolysis, there's required a second step in which the coke should be removed, most probably by combustion. And then we have the oils resulting from it. And this is our chemical recycling setup, which is a stir tank, which capacity is 1 liter, 1.5 kilowatts. And these are the kind of fibers, how clean they are after the process, as well as the oils that we can get out of it. So the process starts characterizing the content of glass fiber or carbon fiber in the composite itself. So we receive the chunks and we remove at lab scale. Obviously, we did it manually, the balsa or the foams, so that we can calcine the whole sample, and by weight difference, we can assess how much glass fiber against resin we had. And after that, we shred the parts, we separate them by flotation, and we perform the pyrolysis test. We evaluated 3 kind of feedstocks, FRP based on epoxy, FRP based on polyester, both for glass fibers, plus epoxy and carbon fibers. We did this evaluation for 2 different technologies, pyrolysis and solvolysis, as said, the one based on fixed bed, the other based on stir tank. And we characterized the fibers and the resulting oil. So there is a huge amount of data that will be released in at least 2 papers in the coming 2 or 3 months. So I cannot share right now specific results, but they can show some tendencies. So for example, if pyrolysis temperatures are too low, we are not able to remove the whole resin as expected. If we can optimize the temperature, we can get fairly clean and aligned fibers. If the temperature is too hot, or we can create hot spots on the system, you can see that we are able even to fuse dot silica. So this is to illustrate how big are the temperature gradients that we can find. In less than 1 millimeter, one part can be at 500 degrees Celsius, and the other part could be even higher than 1,000. So huge temperature differences can be found if the configuration or the arrangement of the bed is not controlled, let's say. And for polyester, as said, the degradation wasn't as much as for epoxy, so 90 against 100%. And so is the fact that we can get the fibers with more coke than those after epoxy. Regarding the oils, interestingly, the content of phenols out of epoxy pyrolysis is more than 80%. That's great because talking to partners in the chemical industry, they are very interested in these oils. And this is a topic that hasn't been discussed before in here, because we were every time talking about fibers. The good news is that oils can also be profitable. In case of polyester, the number of phenols is much lower, of course, but we are getting other interesting molecules, phthalates and phthalic acid derivatives. that are more than 70%. For solvolysis, which is a problem, the very heterogeneous distribution of compounds that we get. So even the highest fraction, which are phenyl derivatives, imply less than 70% in weight. So it's much difficult to get value out of solvolysis oils than from pyrolysis oils. This was regarding glass fibers. In this case, regarding carbon fibers, this is much more interesting even because we do not need any kind of susceptors. The carbon fibers absorb by themselves, and even working at as low temperatures as 150 degrees Celsius that you can see here, we can produce a lot of pyrolysis oil, having a resin conversion of 80% and oil yields beyond 60%. So thinking about the validity of these oils for different purposes, what you see here is the atomic ratio between hydrogen and carbon against oxygen and carbon. This diagram is used normally by people at the petrochemical industry to assess the validity of these oils as an input for the steam cracking. So for the production of fuels. As you can see, jet fuels and diesel do not have any kind of oxygen. There are only paraffins and olefins, simply hydrocarbons. So epoxy and polyester have a lot of oxygen in principle, but after the pyrolysis process, the oxygen content is decreased and we approach that of naphtha and biodiesel. So that's good news if we want to use them as fuels. But as said before, the application of pyrolysis oils for the chemical industry, for the phenol producers industry, is much more convenient, I would say. After that, after the benchmarking of both the pyrolysis and solvolysis technologies, we carried out techno-economic analysis. Of course, these numbers do not say many things because they are based on experiments carried out at the 1 liter scale, but still they can give useful information. If you look at the energy consumption of the different process steps involved in pyrolysis and solvolysis, which are milling, the thermochemical process itself, filtering, purification, you see that the overall consumption of solvolysis is at least 2 times higher than that of pyrolysis. But also, the OPEX and CAPEX of solvolysis is much higher. Why? Because we need to work with fluids as solvents. So we are working at high temperature, relatively high, but especially we are working at very high pressures. Let's say 80 to 100 bar. That means we need reactors with thick walls and very well contained to avoid explosions or whatever. That's why the reactors themselves are much expensive. So based on this, we decided to work on the scaling of microwave pyrolysis technology. And this is the setup that we are currently commissioning at our facilities at Circe, that it's able to process up to 30 kilograms per hour of FRP coming from wind turbine blades. And essentially, you can see there the reactor itself that has been fully designed and modeled and built by us. And also the pre and post processing equipment that it's required for it. So based on preliminary calculations, because as said, we are only at commissioning stage, we would be able to process, sorry, I said 30 is double, it's 60 kilograms per hour. Compared to the 20 grams that we had at bench scale, it's much a lot. But the interesting thing is that the OPEX can be reduced by 58 times, so only 8 euro per kilogram of FRP. Of course, that is 8,000 per ton, which is very far from a commercial, from having a positive business case, but still there's a lot of reduction against a bench scale unit. The CapEx only increased by 5 times regarding the initial investment for the equipment at bench scale. And also the energy consumption of this new setup is 120 times lower than that under bench scale compared to the same unit of FRP treated. So this brings me to the conclusions. The first one is that microwave heating boosts energy efficiency of wind turbine blades recycling, leading to a 3 times at least lower consumption per kilogram of FRP with respect to conventional heating. And it allows us to enhance the process controllability, the oil products distribution, and the reclaimed fibers quality by working at slightly lower temperatures than conventional processes. Both pyrolysis and salt-volysis were evaluated, and techno-economic assessment revealed that the overall cost, CapEx plus OpEx of pyrolysis is roughly 2 times lower than that of salt-volysis. The quality of the fibers are comparable between the processes, and pyrolysis seems to be more interesting from the point of view of the oils obtained. And this new microwave pyrolysis pilot unit is being commissioned to assess the process scalability and to assess how the continuous operation would look like for this kind of waste. So this is our current roadmap. We are somewhere here with the process scaling with the aid of 2 big European projects, Plastis and Refresh, plus also a private funding from our colleagues of Gerwind. And of course, we are now about to face this part that needs private investment. So as soon as we get a relevant amount of money to develop it further from an investor, we can promise to reach the market in a midterm. And yeah, this is commercial, right? And that's all from my side. And thank you very much for being till the end. Yeah, do you have any question? Yeah. Profitability, maybe?
Yeah, thank you very much for that presentation. I do have a question because I have extensive experience with microwave ovens. What if you have a mixture of glass fiber and carbon fibers? And
then you don't need susceptors anymore.
Yeah, but look, glass fiber is an insulator.
Yeah.
Carbon fiber are electrically conductive. And if I put something electrically conductive in a microwave, I get sparks, I get fire. So how do you prevent that?
Look.
Maybe I missed it, but
No.
The other question.
It's a very interesting question.
Yeah. The other question I had was when I was working with microwave, it was very sensitive to moisture of the material I was trying to heat up. Moisture content, big time.
But when you are above 200 degrees Celsius or so, which is the required temperature for pyrolysis, then water is over.
Okay. Yeah, for sure.
But,
yeah, we work with much lower temperatures.
In here, there is a mixture of silica powder.
When you say, I can't see it, sorry.
This is a mixture of silica powder and chunks of carbon fibers. There is no explosion there. There isn't any kind of hotspot or electrical discharge. In this case, we're only putting carbon fibers. And of course, at the tip points, there are points in which the electromagnetic field concentrated and creates hotspots.
Yeah, so those are sparks there. Okay.
Exactly.
So in that top middle photo there, those are sparks, right?
The sparks,
Okay,
yeah.
I would expect that. But you said if it's immersed in the other material, then you can't see
there
them.
are no sparks.
You can't see them. You can't, they'll still be there. I mean, that's physics. Okay.
Well, we use thermal cameras that see through quartz, and this is quartz.
Okay.
Quartz sand, and we don't see any.
Last question, microwaves need to have a certain distance, attuned distance between anode and cathode. So, we had to really tune this in. What's the distance you're using right now? Can you give me a hint? In centimeters, millimeters, whatever. Feet, inches, anything goes.
No, as far as I know, the anode and cathode technology is used for radio frequency, but in here, microwave ovens, they have magnetrons, waveguides, and they release the electromagnetic field within the cavity. So there is no anode and cathode and
Yeah, but still, I'm trying to get to what's the biggest piece you can actually handle.
Piece?
Yeah, what's the size of the material you can actually put in there?
Well, if you shred it and you have something to mix the whole thing, like an auger feeder, so a helicoidal stirrer or whatever, working at frequencies of 915 megahertz, they have a wavelength of 33 centimeters.
Right, okay.
So imagine that the maximum electromagnetic field is within the center of it. So this is the maximum size that you could be able to hit in an homogeneous way.
All right, okay. All right, good, thank you.
Welcome.
Any other questions? Ignacio, thank you very much.
You're welcome.
Well, this concludes our two-day discussion, and I hope you feel invigorated and stimulated with all the conversations. I just have a couple of observations from we've discussed and kind of a point of challenge or consideration. And that is when we look at all the different conversations and ideas and methods and whatnot that we're looking at, it seems like we could be kind of a whiplash for the opportunities that may be out there and the different levels of TR readiness and whatnot. And so one of the things that I find very interesting that's probably fodder or opportunity for future conversations today, tomorrow, the next conference, is looking at questions like LCA and EPD and things like that we haven't really been able to dive into properly. But it's not just what are they or what do they accomplish, it's should we have them or what should it be like if we have them? For example, with an LCA, life cycle assessment, or EPD, environmental product declaration. We've seen in some of the slides the use of these, right, and the discussion of these, but sometimes the values are a little bit different from one method to another or one model to another. The assumptions may be different. And so what do we do with those considerations? Do we think about standardization of LCA? Do we think about keeping it different region by region or industry by industry based upon the assumptions and those particular variables and whatnot, as long as they're duly expressed? Or what about EPDs? Maybe EPDs are a better instrument, so to speak, to measure things when it comes to recovered material going into a new industry. As an example, with an LPD, it might be recovered material, but it may not talk about the process behind that recovered material, but what amount is, say, of virgin materials displaced by that particular LPD product, as an example. So there's, I think, a lot of different ways to think about
these mechanisms that have, say, intrinsic value, but we don't know what to do with them yet. They're still evolving, so to speak. Or even R value. When I say R value, I'm not talking about insulation in your home, heat insulation and whatnot, but I'm talking about kind of the charts that some of you had in your discussions and in your PowerPoint slide presentations. Reuse, repurpose, recovery, things like that. If you're on one side of the pond, as an example, when you're speaking to OEMs and owner operators, what they typically prefer is a separation of resin and glass, and that going into some type of new life cycle product. Because for whatever reason, there may be a perspective that cement kiln co-processing is not ideal, or repurposing for street furniture or something like this is not the best thing to do. Whereas we've seen on this side of the pond and in the discussion in the last couple of days, maybe those types of repurposing projects or those types of recovery processes for going back into infrastructure might be better suited. I think there's something that we could articulate maybe in the abstract, but bring it down into the tangible. The abstract would be, what is the best situation and scenario? What is the ideal? And then what is realistically what the market can support and where we are kind of with business practices and models and whatnot. So the ideal, probably all of us would say, is we would have a continuous glass fiber filament that would go into next generation SMC, BMC, non-woven mats, thermoplastic pallets, et cetera, additive manufacturing to support automotive, aerospace, wind, all the different industries. But then what is the real? Maybe the real is very, very different than what the ideal is. And how do we navigate or negotiate, those different interests when it comes to energy to take to process the materials, when it comes to logistics to move these materials around, when it comes to, say, intake fees or offtake fees to process everything. There's so many different considerations that businesses look at, academics look at, the government officials look at, and it takes a conversation for all of us. Just like I mentioned yesterday, one of my most productive, say, business conversations when it came to supply chain is when you have procurement, sustainability, and head of engineering, and head of business development, head of marketing, all in the same call, all in the same room. That's ideal, and it doesn't really happen. So even that's ideal. What is the real? You might talk with procurement and that's it. And they may not even speak to business development or CFO about if it's feasible or not. So there's so many different considerations and other conversations that can be had, but we need to do tangible things. We need to move the conversation and advance everything forward to some degree. So one of the things that I suggest is maybe a tangible could be a scenario. Imagine with me, if you will, if you have a very interesting incentive or credit instrument whereby you have the OEMs, some are here, of course, and you have the owner operators, some are also here as well. And maybe you have a cost share gate fee or end of life fee associated with the purchase of every single wind blade. And that fee goes into something that we all know as a financial institution, a bank, an escrow account, a trading platform. So at the point that that particular blade or that particular wind farm is decommissioned, you take the fee that is cost shared for that blade price that goes into the escrow, the trading platform or whatnot, that goes to the recycling agent. And then you take the interest on that account, and that is shared between the OEM and the owner operator, the asset manager. And so that is something that we already have in place with financial institutions. Those types of instruments are tried and true for hundreds of years, of course. And so with something in place like that, you have an immediate budget, if you will, that's incentivized to make sure that every single blade has a new home. That new home may be a concrete foundation, or that new home may be some type of building material. That new home may be a filament that is ultimately from recycled materials and goes into, to the glass fiber OEMs and into a continuous filament. So I want us to be very creative when we think about these ideas. Let's use existing instruments, institutions, infrastructure that's already in place and leverage those effectively and economically so that we can move the conversation along. So I was a joy to be here the last couple of days with many of you. Some are kind of old friends, so to speak. We see each other at conferences and trade shows and whatnot, and some are new individuals and friends and acquaintances. So look forward to the next time we can all meet. And what would be tragic is the next time we meet, we're at the same conversation. What would be fantastic is we have incredible advances in the academic side and in the nonprofit side and in the private business side and in the government sector to move all these conversations along. So I encourage you to advance the conversation over the coming months. Thank you very much.
Ladies and gentlemen, just few last words from my side. Let me thank everyone, our speakers and our attendees for coming, our speakers for sharing the interesting presentations, our participants for asking the questions and getting engaged in the discussions and creating all the atmosphere. I would like to remind you of our evaluation form. Please rate our speakers, the organization, and everything. If you still have time, you can still stay in the lobby. There is still the unlimited coffee and still a few of the snacks. And it was a pleasure to be here with you. I wish you a safe journey home and looking forward to meeting you in one of our upcoming conferences. Thank you and goodbye.